Physicists are measuring one number right now that decides how the whole universe ends. They write it as W, and its value sits close to -1. Whether it rests a hair above that line or a hair below changes the fate of every galaxy, every atom, and time itself. Below -1, everything is torn apart in about 22 billion years. At exactly -1, the cosmos drifts into an endless cold where nothing new can ever happen. Above it, the expansion could someday reverse and pull it all back together. So tonight, stay with me, and we'll follow that one number all the way out. What is beyond the end of the universe? We start with the violent ending, follow it into a sky with no stars, and reach a future so long that everything that ever existed is assembled again from nothing. Before we begin, if you feel even a little curious, a gentle like or a quiet tap on subscribe would truly mean a great deal to me. It may seem like a small gesture, but I'm genuinely grateful for it. Your support helps keep these quiet stories alive and reminds me that somewhere out there, kind and curious minds are still listening. Now, let's begin. The universe is under no obligation to end. Whether it finishes at all was never written into the fabric of things as a promise or a verdict. It was left open as a question physics could in principle answer, and the answer was folded into a single equation set down more than 100 years ago by a man who did not live long enough to learn whether he was right. Everything comes down to a contest between two things you already know from ordinary life. One is the outward drift of space, the slow growth of the distance between any two galaxies that are not bound together. The other is gravity, the patient inward pull of everything that carries mass. If the outward drift wins for good, the universe keeps expanding and cools toward an ending by dilution. If gravity wins, the expansion slows, stops, reverses, and everything falls back together. The future of the cosmos is the outcome of that one tug of war, and none of it is settled in advance. To turn that contest into something we can calculate, we need a way to measure how fast space is stretching. Physicists use a quantity called the Hubble rate, written as h, and its definition is gentler than its reputation. You take the speed at which two galaxies drift apart and divide it by the distance between them. In symbols, h equals a dot over a, where a stands for the size of space and a dot for how quickly that size is changing. Today that rate is small but real. Across every 3.25 million light-years of empty space, the separation widens by about 70 kilometers each second. Up close, it looks like nothing at all. Spread across billions of light-years, it becomes the motion that carries whole galaxies away from one another. Alexander Friedmann took Albert Einstein's theory of gravity and asked what it allowed this rate to do across the whole life of the universe. In 1922, he found one compact relation that still sits at the center of cosmology. You can write it as h squared equals 8 pi g over 3 times the density of the universe, minus a term for the curvature of space. That curvature term carries one of 3 signs: for space that bends closed, stays flat, or bends open. In plain words, the speed of expansion is set by 2 things pulling against each other: how much the universe contains, which drags the expansion down through gravity, and how space itself is bent, which can tilt the balance either way. One equation, and the entire fate of everything lives inside it. Hidden in that relation is a single dividing line, one particular density that separates the two endings. We call it the critical density, and it comes out to 3 times the Hubble rate squared, divided by 8 pi times Newton's gravitational constant. The number is almost unbelievably small. It works out to roughly 5 or 6 hydrogen atoms in every cubic meter of space. Ordinary air tells the opposite story. Each cubic meter of it holds something like 25 trillion molecules, packed shoulder to shoulder by comparison. The average cubic meter of the cosmos holds about 6 atoms, and the fate of absolutely everything hangs on whether that count runs a little above 6 or a little below it. In a universe built only of matter, gravity can pull but never push, so the expansion can only slow. The one question is whether that slowing ever deepens into a full stop. If the real density sits above the critical line, gravity has enough to work with. Space closes, curved back on itself like the surface of a globe, and the expansion is bound to stall and reverse into a collapse. If the density falls below the line, gravity never gathers enough grip, space stays open, and the growth runs on without end. And if the universe balances exactly on the line, its geometry is flat and it drifts outward forever, while slowing toward a stillness it never quite reaches. 3 densities, 3 shapes for space, 3 endings, all of it folded into one relation and one number. A fair objection arrives here, the same one that occurred to nearly everyone who first met these ideas. If the answer is only a matter of counting the matter in a box, then we should be able to add up the galaxies and the gas and the dark matter, set the total against that critical value, and read the ending straight off. We can go further and measure the shape of space itself, and when we do, it comes back almost perfectly flat. Light that has crossed billions of years reaches us along paths that have barely bent. By the matter-only reasoning, a flat universe sits right on the dividing line, coasting outward forever while slowing toward a rest it never reaches. It is a clean answer. The trouble is that the matter never adds up to that flat, balanced total. Count everything that pulls, and you reach only about 1/3 of what a flat universe demands. And beneath that gap lies an assumption almost no one thought to challenge. Friedmann's balance, in its first form, pictures a universe filled only with matter and radiation, with things that pull inward and nothing that pushes outward on its own. That quiet assumption is the hinge the whole ending turns on. The physics here is settled and clean. The story of the man who found it is neither, and that is the part that has always held me. When Friedmann first sent his moving universe out into the world, Albert Einstein, whose own theory had made the work possible, refused to believe it. In 1922, Einstein published a short note declaring that Friedmann's solution held a mathematical mistake. Friedmann wrote back with the calculation laid out line by line and passed it to a colleague traveling to Berlin. Einstein was touring Japan and did not read the reply for months. When he finally worked through it in 1923, he retracted his objection in print and admitted the error had been his own. The man who taught the universe how to bend space could not, at first, believe his own equations would let it move. I find that reluctance easy to forgive. A universe that holds perfectly still is the more comfortable thing to believe. A universe that expands is one with a history, and a universe with a history is one that can have an ending. Friedman did not flinch from that. 2 years later, in a second paper, he worked out a version of space with negative curvature, an open universe that expands eternally and never returns. He had mapped both roads himself, the one that circles back and the one that runs on forever. One of his biographers later reached for the largest comparison he could find, and the sense of it was this. As Copernicus had pried the Earth loose from the center and set it turning around the sun, Friedman had pried the whole universe loose and set it expanding. That is no small thing to have done with a piece of chalk and a page of equations. He did it, and then he was gone. Friedman died in 1925 at the age of 37 of typhoid fever, most likely carried by an unwashed pair. He ate at a railway station on his way home from his honeymoon in Crimea. He died 4 years before Edwin Hubble gathered the first firm evidence that the universe really is expanding, so not one measurement ever reached him to confirm the thing he had proved was possible. He liked to quote a line from Dante about sailing into waters no one had crossed before, and it suits him almost too well. He handed us the machine that decides whether everything ends, showed us it had at least 3 settings, and stepped away before the first reading ever came back. That equation is more than a century old now, and we carry instruments Friedman could not have imagined. Spacecraft riding above the atmosphere and detectors that catch light from the far edge of the visible universe. We can weigh the cosmos far more finely than anyone in his lifetime. And still, when we finish counting all the matter and hold the total up against his critical line, the sum does not tell us how the universe ends. So why, 100 years and a sky full of telescopes later, does counting everything in the universe still fail to tell us how it ends? Geometry does not decide how the universe ends. The shape of space looked like the whole answer, and it was not. A second ingredient had been sitting inside the equations the entire time, and when it finally spoke, it overruled the curvature completely. We left the last stretch with a gap that would not close. Add up every galaxy, every cloud of gas, and all the unseen dark matter that outweighs the stars, and the total reaches only about 1/3 of what a flat universe requires. Space measures flat, yet the matter to make it flat is 2/3 missing. For a while, the honest response was to assume we had simply not found the rest. The rest was never matter at all. The missing 2/3 is energy that belongs to space itself. Every cubic meter of empty space appears to carry a small, fixed amount of energy, the same in the gap between galaxies as in the space drifting through this room. Physicists fold it into Friedman's equation as an extra term, a constant written with the Greek letter lambda, and its effect runs opposite to gravity's. Where matter pulls the expansion down, this term pushes it up. Set out the full budget, and the strangeness sharpens. Ordinary atoms, everything that glows or reflects or can be held in a hand, make up only about 5% of the whole. Dark matter, unseen and silent, adds roughly 1/4 more. The remaining portion, close to 70%, is this energy of empty space. Everything you have ever seen sits as a thin trace on the surface of a universe ruled by 2 things no one has ever directly laid eyes on. The story of how it all ends is being written almost entirely by the part of the cosmos we understand least. Measured out, that energy is faint past belief, something near the mass of a few hydrogen atoms spread across each cubic meter. Locally, it amounts to nothing. Stretched across the entire volume of the cosmos, and never once thinning as that volume grows, it becomes the heaviest presence there is. What makes this energy overrule everything else is a piece of simple accounting. Matter thins out as the universe grows. Double the size of space, and the same galaxies are spread through 8 times the volume. So the density of matter falls as the cube of the expansion. In symbols, the density of matter drops as 1 over a cubed, where A is again the size of space. The energy of empty space does none of this. It is a property of the space itself, so every new cubic meter that expansion creates arrives carrying its own fixed dose of it. Matter dilutes toward nothing while this energy holds perfectly steady. Given enough time, the steady thing must win over the fading thing, no matter which one started out ahead. Once you grant that, the old link between shape and fate comes apart. A closed universe, curved back on itself, was supposed to be doomed to recollapse. Give it enough of this vacuum energy, and it expands forever instead. An open universe was supposed to expand forever, no matter what. The vacuum energy makes it expand faster and accelerate as it goes. For half a century, the central question about the ending was posed as a question about shape. Is space closed and bound to fall back, or open and bound to fly apart? The vacuum energy quietly retired that question. The shape of space became a thing to measure for its own sake, and the fate of everything became a question about what fills the emptiest parts of it. There is something strange in the way this energy pushes. Ordinary things gravitate because they hold mass and energy, and gravity from mass and energy always pulls inward. The vacuum energy holds energy too, so on its own that piece would also pull. What flips the sign is its pressure. This energy carries a pressure that is negative, a tension that draws inward on the walls of any volume rather than pressing outward. And in Einstein's gravity, pressure gravitates alongside energy. A large enough negative pressure turns the net gravitational effect repulsive, which is why the expansion speeds up rather than slows. That negativity is not an extra assumption bolted on from outside. It follows from the energy staying constant. When space expands, it does work, and the first law of thermodynamics ties that work to pressure through a simple relation that the change in energy equals minus the pressure times the change in volume. For an ordinary gas, expansion drains energy, and the pressure comes out positive. For an energy whose density refuses to fall as the volume grows, the books only balance if the pressure is negative. The vacuum drives the expansion outward for the very reason that it keeps the same energy in every cubic meter. How negative that pressure runs, set against the energy behind it, becomes the number that decides everything from here. The history of this term reads almost as a comedy of misjudgment, and Albert Einstein sits at the center of it. He wrote lambda into his equations in 1917 for a reason that now feels poignant. He wanted the universe to stand still. His own theory kept describing a cosmos that had to move, expanding or contracting, and a restless universe unsettled him. So he added the lambda term by hand, tuned to cancel gravity exactly and hold everything in a frozen balance. When Edwin Hubble's measurements showed the universe expanding after all, the reason for the term drained away, and Einstein discarded it. As George Gamow later told the story, Einstein came to call the whole affair the biggest blunder of his life. What stays with me is not the mistake. It is that the term he added for the wrong reason and then threw away in embarrassment is now the leading candidate for how the universe ends. He put it in to stop the cosmos from having a history. It returned as the thing that may decide the cosmos's final chapter. The mistake was never the lambda itself. It was the belief that he could decide in advance what the universe would be allowed to do. One person read the term correctly, while nearly everyone else argued over whether to keep it. Georges Lemaitre, the Belgian priest and physicist who had already worked out the expansion on his own, looked at lambda and saw a real energy of empty space where others saw only a convenient fix. In 1934, he proposed that lambda measures the energy density of the vacuum, the same idea sitting under dark energy today. He estimated its size and moved on. Almost no one followed. His paper drew only a few dozen citations across the next half-century, and through much of the 1950s and 60s, it was cited not once. The interpretation that now anchors modern cosmology sat in print, correct and unread, for the better part of a lifetime. There is a quiet lesson in that, and it has little to do with physics. Being right early can mean being ignored for 50 years. Lemaitre had the answer before the world had any place to put it, and the measurements did not catch up to him until the 1990s. Truth can wait a long time in a footnote before anyone is ready to read it. Richard C. Tolman gave the whole question its rigor. In 1934, the same year Lemaitre was reinterpreting lambda, Tolman treated the expanding universe as a thermodynamic system in its own right, bound by the same laws of heat and entropy that govern a steam engine or a cooling cup of coffee. He showed that the field equations and the second law of thermodynamics, working together, are what fix the possible fates of the cosmos. That reframing turned the ending from a thing we could only imagine into a thing we could calculate. With that, the fate of the universe no longer hangs on the shape of space. It hangs on the energy of empty space, on how much of it there is, and, above everything, on how hard it pushes. The whole question now funnels down to that second property, the relationship between the pressure of this vacuum energy and its density. Physicists give that relationship a single letter and a single number. So if the ending now rests on how hard empty space pushes, what has that push been measured to be, and why should a single decimal place stand between a universe that quietly fades and a universe that tears itself to pieces? The universe has three possible endings, and which one it gets comes down to whether a single number sits above, exactly on, or below the value -1. That number is not exotic. It is a ratio, the pressure of a thing divided by its energy density, and physicists write it as the letter W. Every substance in the cosmos carries its own value of W, and the value tells you how that substance behaves when space stretches. For ordinary matter, the kind with mass sitting more or less still, the pressure is negligible next to the energy locked in that mass, so W is essentially zero. For radiation, for light itself, the pressure comes to a third of the energy density, so W is 1/3. For the energy of empty space we met a moment ago, the pressure is neither small nor positive. It is equal and opposite to the density, which sets W at -1. That one value, -1, holds the whole story, and to see why we need the rule that ties W to the fate of a substance as the universe grows. We built the pieces of it already. The first law of thermodynamics said that when space expands and does work, the energy inside changes in step with the pressure. Carry that through, and you get a single clean relation. The density of any substance falls as the size of space raised to the power of -3 times the quantity 1 plus W. Written plainly, density scales as a to the power of -3 times 1 plus W. That formula looks dry until you start feeding numbers into it. For matter, W is 0, so 1 plus W is 1, and the density drops as 1 over a cubed. Double the universe and matter thins to an eighth, exactly as you would expect for stuff spread through a growing volume. For radiation, W is a third, 1 plus W is 4/3, and the density falls as 1 over a to the 4th. Light thins even faster than matter, because expansion stretches each wave and drains its energy on top of the dilution. When you put -1 into that formula, it does something the other cases never do. 1 plus W becomes 0. -3 times 0 is 0, and the size of space raised to the 0 power is 1. The density does not change at all. However far space stretches, this energy holds exactly the same value in every cubic meter, forever. -1 is the single value where the exponent vanishes, the knife edge between a density that fades and a density that grows. This is why dark energy arrived so late to power. The story reads cleanly in those exponents. Radiation, thinning as 1 over a to the 4th, ruled the first few tens of thousands of years and then faded fastest of all. Matter, thinning as 1 over a cubed, took over and gathered itself into galaxies. The vacuum energy, thinning not at all, simply waited. For most of cosmic history, it was a rounding error, a whisper beneath the matter. But a density that never falls cannot be outrun forever by densities that do. Roughly 4 billion years ago, the vacuum's steady density finally overtook the thinning matter, though its push had already tipped the expansion into acceleration a couple of billion years earlier. We happen to be living in the first age it rules. Stranger still, the two densities still run within a factor of a few of each other today, a near balance no one has fully explained. Everything about the ending lives on the two sides of that knife edge. With WA a little above -1, at -9/10, 1 plus W is a small positive number. The density still falls, only very slowly, as space expands. The outward push weakens over the ages. The universe keeps growing and thinning without limit, and nothing is ever torn apart. This gentler kind of dark energy carries a name borrowed from the ancients, quintessence, after the fifth element the Greeks imagined beyond earth, water, air, and fire. With W a little below -1 instead, at -1.5, 1 plus W turns negative. -3 times a negative number is positive, and the density climbs as space grows, rising as a to the power of 1.5. Every new cubic meter of space brings more of this energy than the last, so the push does not hold steady and does not weaken. It strengthens without bound. Robert Caldwell gave this darker possibility its name in the late 1990s. He called it phantom energy. I have always liked that name for how honestly strange it is. Phantom energy breaks one of the quiet assumptions physicists lean on, that pressure and density stay within certain bounds, the conditions that ordinary matter and light always obey. To climb as space grows, it has to pack more total energy into a larger volume than it held in a smaller one, behavior no ordinary substance ever shows. It acts like something that should not be permitted, and yet the equations allow it, and the measurements have never quite ruled it out. Someone reached for the word phantom half in warning and half in fascination, and it stuck because it fit. A second threshold sits inside the same formula, and it explains why any of this pushes at all. The acceleration of the universe depends on the density added to 3 times the pressure. Work that through with W, and you find that expansion speeds up whenever W drops below -1/3. So -1/3 is the line where a substance stops slowing the universe and starts driving it apart. -1 is the deeper line. -1/3 only tells you the expansion speeds up. -1 tells you whether that speeding ever runs away with itself. Between those two values, from -1/3 down toward -1, the universe accelerates, but gradually eases off. Below -1, the acceleration feeds on itself. We should be honest about where this number even comes from. No instrument can be lowered into the vacuum to read its pressure off a gauge. We infer W from the shape of the expansion itself, from the way distant exploding stars appear dimmer or brighter than a steady push would predict, and from how the vast scaffolding of galaxies has grown across billions of years. The value of W is read backward out of the history of the sky. That indirectness is the reason the answer has stayed uncertain for so long, and the reason a small shift in the data can move the ending from one branch to another. The value -1 is exactly the cosmological constant, the steady vacuum energy Georges Lemaitre read out of the equations 90 years ago. A universe resting precisely on -1 expands forever at a constant, relentless pace, never fading and never exploding. A universe just above it drifts into a long, thinning cold. A universe just below it races toward a violent finish. 3 values, 3 destinies, all of them balanced on the second and third decimal place of a single ratio. There is a part of me that resists letting the ending of everything rest on a fraction. It feels too small, too arbitrary, for a question that large. And yet that is the honest shape of the answer. The difference between a cosmos that dies gently and one that is torn to shreds is not a matter of grand forces or hidden purpose. It comes down to whether one measured number lands at -1 1/100th or -99 hundredths. Nature does not seem to care how modest the deciding quantity looks. All of this assumes W holds still, that whatever fills empty space keeps the same character for the rest of time. If it does, those 3 fates are the entire menu. Whether it does is a question we will have to return to, because the newest measurements have started to drift in a way almost no one expected. For now, the most alarming branch is the one below the line, where the density of empty space climbs without end. A push that strengthens the more room it is given does not slow as it grows. It gathers speed. So if the energy driving the universe apart can feed on the very expansion it creates, what stops it? And what is left of a galaxy, a star, or a single atom when nothing does? only one of the three endings truly ends. The others run on forever, one fading into cold and one looping back on itself. This one stops, and when it stops, it takes space and time down with it. Behind it runs the feedback loop we glimpsed in that scaling law. Below -1, the density of empty space climbs as the universe expands. A larger universe holds more of this energy, and more of this energy means a stronger outward push, and a stronger push makes the universe larger still. Each turn of that wheel feeds the next. The expansion does not settle into a steady pace the way a constant vacuum energy would. It accelerates, and the acceleration itself accelerates. The Hubble rate, the measure of how fast space stretches, does not level off. It climbs toward infinity, and it reaches infinity in a finite amount of time. Its pace shows the same thing from another angle, through the doubling time. Under a constant vacuum energy, the universe doubles in size over a fixed stretch, the same length every time. Under phantom energy, each doubling takes less time than the one before, and those intervals shrink toward zero. The universe does not only grow, the growing itself speeds up until near the end space doubles again and again in less and less time, and then in almost no time at all. In the last stretch, the doublings might come in a year, then a day, then a heartbeat, then faster than any clock can mark, piling up without limit as the deadline arrives. That last part is where the ordinary picture breaks. A universe ruled by a constant vacuum energy also expands forever, exponentially, yet its expansion rate stays fixed and small. Locally, nothing notices. The galaxy holds, the sun holds, your own body holds, because the pull of expansion across anything that's small is far too gentle to matter. The numbers make the gap plain. The outward tug of expansion across the width of the solar system today is weaker than the sun's gravitational hold by a factor with dozens of zeros in it. Phantom energy erases that safety. As the Hubble rate climbs without bound, that tiny tug does not stay tiny. It grows until the stretch across smaller and smaller distances overpowers the forces that hold things together. One clean way to see it is through the horizon, the distance beyond which space is receding faster than any signal or force can cross. This does not break relativity. Nothing travels through space faster than light. Space itself expands, and the gap between two distant points can widen faster than light can bridge it, which is why a force reaching from one point to the other can simply run out of room. In a runaway expansion, that horizon does not stay put. It shrinks. When it shrinks below the size of a structure, the far side of that structure falls out of reach of the near side, and no force can hold together two things that can no longer send anything to each other. One by one, the forces lose their reach, the long arm of gravity first, then the electric bonds of chemistry, then the fierce short grip that holds a nucleus, each severed as the horizon shrinks past its scale. The horizon closes in like a tightening circle, and everything larger than the circle comes apart. In order, from the greatest structures down to the smallest. The time you have before that circle reaches you follows a simple rule. It is set by how far 10 falls below -1, by the present rate of expansion, and by how much matter still weighs on the balance. Push W toward -1, and the deadline slides toward never. At exactly -1, the deadline never arrives at all. Move W down to -1.5, and it collapses to about 22 billion years, the soonest the universe could plausibly end. Caldwell and his colleagues worked out the full schedule for that value. For most of those 22 billion years, almost nothing seems wrong. If that were our future, the universe would already be nearly 40% through its entire lifespan, with roughly 22 of some 36 billion years still ahead. Then, in the final stretch, the tearing begins and races down the ladder of scale. The order is not arbitrary. The largest structures are the most loosely bound for their size, held only by the faint long pull of gravity across enormous distances, so they give way first. The tight electric and nuclear bonds inside matter are far stronger, and they hold until the final instance. Around 200 million years before the end, the clusters of galaxies are pulled apart. About 60 million years before, gravity can no longer hold the Milky Way together, and it disperses. Roughly 3 months before the end, the Sun loses its grip on its planets, and the solar system comes unbound. About 30 minutes before, the Earth itself is torn open. And in the last fraction of a second, something near 1/10 of a billionth of a second before the end, the atoms are stripped apart, electrons first, then the nuclei inside them. At the final instant, the scale factor becomes infinite, and space and time are ripped apart with everything else. What unsettles me most here is not the destruction. It is the schedule. A world in the path of this ending would sail through billions of untroubled years, then lose its galaxy, its star, and its ground in the span of a single lifetime, and lose everything smaller than that in the last half hour. There is almost no warning built into it. The universe looks calm right up until the moment it does not, and then the unraveling is nearly instant. This branch answers the question in the plainest way of the three. What lies beyond this ending is not darkness or cold or a new beginning. There is no beyond at all. At the moment of the rip, the scale factor is infinite, and the equations that bind space and time together stop returning any answer. Physicists call that a singularity. That is what sets this ending apart from the other two. A universe that fades into cold still has time left to it. A universe that collapses and rebounds still has time. Here, time is one of the casualties. Whatever the word beyond is meant to point at, it needs a where and a when in order to be beyond anything, and the rip leaves neither. Even now, I want to believe something waits on the far side of it, that cold and dark would at least be a place to stand. This ending withholds even that. The three physicists who mapped this called it a cosmic doomsday, and the name has stuck. Robert Caldwell, Mark Kamionkovsky, and Nevin Weinberg published the work in 2003. Laying out the runaway and the countdown in careful detail. In the same breath, they were clear that it was a hypothetical example and not a forecast. The evidence, even then, placed W very close to -1, close enough that the gentle constant sat squarely inside the range of what the data allowed. Softer cousins of this fate exist as well. Later theorists found versions where the density of empty space still climbs and still tears galaxies and atoms apart in the same order, yet stretches the whole process across an infinite future so that no single final instant ever comes. a rip with no deadline. In those models, the destruction is just as complete, only it never quite finishes. That reassures me more than it probably should. The people who worked out the most violent death the universe can suffer were also the first to say it may never come. They built the doomsday clock, then pointed out that its hands might never move. There is a discipline in that I admire, following an idea all the way to its worst conclusion and then refusing to oversell it. Everything then hangs on whether W is truly below -1 or merely near it. 22 billion years is longer than the universe has already lived, so even the soonest possible ending lies further off than the whole of the past. That is cold comfort, but it is comfort. The gap between a universe that lasts forever and one with a deadline is a single step across that line, a difference buried in the second decimal place of a number no eye can see. So how do you weigh the pressure of empty space precisely enough to know whether it rests at -1 or a hair beneath it, when the answer is a deadline no telescope was ever built to read? We measure the fate of everything by the light of stars that tore themselves apart billions of years ago. There is no gauge to lower into the vacuum, no dial that reads out W. The number has to be rebuilt from the past, and the most reliable record of the past we hold is the brightness of a particular kind of dying star. The idea rests on a piece of physics simple enough to feel in the palm of a hand. Light spreads as it travels, thinning over the surface of an ever larger sphere. Double the distance to a source, and its light is spread over 4 times the area, so it looks 4 times fainter. The brightness you receive falls as 1 over the distance squared. Turn that around, and if you know how bright something truly is, then how bright it looks tells you exactly how far away it sits. A flame of known strength becomes a ruler. A catch sits at the center of it, the matter of knowing the true brightness. A faint point in the sky could be a dim source close by, or a brilliant one far away, and from the light alone you cannot tell which. What astronomers needed was a class of objects that all shine with nearly the same true brightness, everywhere, across all of cosmic history. They found one in the death of a certain kind of star. A white dwarf is the cooling core left behind when a star like the Sun runs out of fuel. It does not collapse, because the electrons packed inside it push back through a purely quantum effect, a pressure that exists for the simple reason that 2 electrons refuse to occupy the same state. But that pressure has a ceiling. Subramanian Chandrasekhar worked out, as a young man on the long sea voyage from India to England, that once a white dwarf's mass passes about 1 4/10 times the mass of the Sun, its electrons are forced to move so close to the speed of light that their pressure can no longer hold. Above that mass, the star has no way to support itself, and it collapses and detonates. He was 19, and the ceiling he found was doubted for years by some of the most respected astronomers alive, before the stars themselves proved him right. That threshold is the gift. Because every one of these stars crosses the same line at the same mass, they explode with very nearly the same power. At its peak, a single one blazes with a light of about 5 billion suns, bright enough to briefly outshine an entire galaxy of 100 billion stars and to be picked out across billions of light years. They are the same everywhere, and they are visible almost everywhere. A ruler you can lay across half the universe. They are not perfectly identical, and honesty requires saying so. The brighter ones fade a little more slowly, and astronomers learn to read that link between brightness and the shape of the fading light, correcting each supernova back to a common standard. Once calibrated, their spread in true brightness shrinks to a fraction, tight enough to measure distances across the cosmos to within a few percent. Distance is only half of what each supernova tells us. The other half is written in its color. As light crosses an expanding universe, its waves are stretched along with space itself, shifted toward the red. How far the light has been stretched is a direct read on how much the universe has grown since it left. 1 plus that redshift equals 1 over the scale factor, the very quantity that has run through all of this. So a supernova's redshift reveals the size of the universe on the day its light set out. Put distance and redshift together for supernovae near and far, and you are no longer looking at single stars. You are watching the expansion history of the universe unfold. That bend is faint, and it is why the discovery took so long. Nearby, distance and redshift track each other in a simple straight line. The whole story of dark energy lives in a slight departure from that line, at great distances, a dimming of only a few percent. To trust a few percent, astronomers needed hundreds of these supernovae, each one calibrated, each one a dead star found, watched as it brightened and faded, and pinned to a distance. The evidence for the fate of everything is gathered one exploded star at a time. In the late 1990s, 2 teams set out to measure that history, expecting to catch the expansion gradually slowing. Everyone assumed gravity was quietly pulling the brakes, and the only question was how hard. The distant supernovae came back fainter than a slowing universe could explain. Fainter meant farther, and farther meant the universe had expanded more than a decelerating cosmos ever would. The expansion was not slowing. It was speeding up. Saul Perlmutter led one team, Brian Schmidt and Adam Rees the other, and they arrived at the same impossible answer independently in the same year. The 3 shared the Nobel Prize in 2011. It still amazes me that the surprise arrived twice. 2 rival groups, chasing the same measurement with different stars and different methods, both set out to time the universe dying slowly, and both found it doing the opposite. When an answer that overturns everything shows up in 2 independent places at once, it stops feeling like a mistake and starts feeling like the sky telling you something plainly. Supernovae alone, though, cannot pin down W by themselves. The same curve of brightness against distance can be fit by more than one blend of matter and dark energy, so the measurement leaves a smear of possible answers along a diagonal rather than a single point. To sharpen it, cosmologists bring in 2 more witnesses that go blind in different directions, so that where one is uncertain, another is sharp. One witness is the afterglow of the Big Bang, the faint microwave glow left over from when the universe was under 400,000 years old. Frozen into its pattern are the overall geometry of space and the exact recipe of matter and radiation at that early time. It anchors the far end of the expansion history with great precision, long before dark energy came to matter at all. Its partner is a ruler hidden in the arrangement of the galaxies. In the hot plasma of the infant universe, sound waves rang out and then froze in place as the cosmos cooled, leaving a preferred separation between galaxies about 500 million light-years across. Because that true length is known, its apparent size at different distances gives the expansion a second reading, the mirror image of the standard candle. A candle of known brightness tells you distance by how faint it looks. A ruler of known length tells you distance by how small it looks. One reads the recent universe, the other reaches deep into the early one. Where the three cross, the smear collapses to a point. Each is half blind on its own, and together they see. For about 20 years, every time these three were laid over one another, they pointed to the same quiet answer. The value of W sat at -1, give or take a few hundredths. A plain, steady cosmological constant, the same vacuum energy Lemaitre had read out of the equations long before anyone could measure it, now sitting right where a constant should. The gentle ending, the long, cool drift, rather than the violent tear, looked like the safe bet. The number that decides everything had settled down, and for 2 decades, it stayed settled. Our yardstick for the end of all things is, fittingly, a catastrophe. Every point on that graph, every measurement narrowing the fate of the cosmos, is a star that died in fire so far away and so long ago that its light is only reaching us now. There is something almost tender in that, reading the death of everything by the light of countless individual deaths, each one a small rehearsal of the ending we are trying to time. The steadiness held right up until it did not. Beginning in 2024, a survey built to map that early universe ruler across millions of galaxies started returning a number that a simple constant would not have predicted. So what did the newest and largest map of the expanding universe see that 20 years of steadiness had not? And why has it left the ending unsettled all over again? The number that it held at -1 for 20 years has started, very slightly, to move. Not by much, and not beyond doubt, yet the newest and largest map of the universe no longer points cleanly at a constant. It leans, for the first time, toward a dark energy that changes. This map comes from an instrument called DESI, the Dark Energy Spectroscopic Instrument, mounted on a 4-meter telescope on a mountaintop in Arizona. Its focal plane carries 5,000 tiny optical fibers, each steered by its own robot, so that in a single pointing, it can gather the light of 5,000 galaxies at once and read the redshift of every one. Over its first years, it has measured distances to some 14 million galaxies and quasars, the largest 3-dimensional map of the cosmos ever made. It was built to read that early universe ruler, the frozen sound wave in the spacing of the galaxies across billions of years of expansion. Laid over the microwave afterglow and the exploding stars, that ruler tells a story a plain constant does not quite fit. On its own, DESI's data sit comfortably with a steady vacuum energy. The strain appears only when the 3 witnesses are combined. Together they prefer a dark energy whose push has not held steady across cosmic time. A model where W drifts fits the measurements better than a model where W stays nailed to -1. At heart, the signal lives in a mismatch. DESI's ruler traces how fast space was stretching at a range of middle distances. The supernovae trace the more recent expansion, and the microwave afterglow fixes the earliest. Read through a single, unchanging constant. Those 3 do not quite agree with one another. Let W drift, and the disagreement softens. That easing is the whole of the evidence, which is also why the result leans so heavily on exactly which data are folded together. It first surfaced in 2024 in DESI's opening data release, drawn from 6 million galaxies. Many expected it to melt away as more data arrived. It did the opposite. When the second release landed in the spring of 2025, with 14 million galaxies behind it, the preference for a changing dark energy had grown rather than faded. A signal that strengthens as the data pile up is the kind that is harder to wave off as noise. Cosmologists let W change in a deliberately simple way. They write it as W of A equals W naught plus WA times the quantity 1 minus A, where A is again the size of space. Today, with A equal to 1, the 1 minus A term vanishes, and W equals W naught, the value right now. In the past, when A was smaller, that term switched on, and WA set how different the push was back then. Two numbers, one for the present and one for the drift. The form has a name, the Chevalier-Polarsky-Linder parametrization, after the physicists who wrote it down, and it has become the standard way to ask whether the vacuum's push has changed. The preferred values point in a direction almost no one expected. W naught comes out above -1, somewhere near -8/10, which would place dark energy today in the gentler quintessence camp, not the phantom that tears. But WA comes out solidly negative, meaning the push was stronger in the past, below -1 in phantom territory. Read together, the two numbers sketch a dark energy that was fierce long ago, crossed the line at -1, somewhere along the way, and has been weakening ever since. Its density seems to have peaked when the universe was about 2/3 its present size, and to be fading now. The simplest way to picture such a thing is a field that was once held taut and is now slowly relaxing, its stored energy draining as it unwinds, the push it exerts easing year by year. That crossing is a puzzle in its own right. A single, simple field filling space finds it very hard to pass through -1 at all because the mathematics resists it. Slipping across the line usually demands something more elaborate, two fields working against each other, or physics we do not yet have in hand. So the data are not merely asking us to give up the constant. They are pointing toward a vacuum stranger than either of the tidy options we started with. If that picture holds, it quietly rewrites the ending. A dark energy resting above -1 today is not on the runaway road to a big rip. The violent tear recedes into unlikelihood. And a dark energy that is weakening rather than holding steady raises a possibility nearly everyone had shelved. If the push keeps fading, gravity may not stay overruled forever, and the ending we crossed off earlier, the one where everything falls back together, edges its way back onto the table. Beyond the ending, the stakes run deeper still. For 25 years, the standard model of cosmology has held together with a single unchanging constant at its heart. If dark energy truly evolves, that is the first serious crack in that model in a generation, and it would drag a much older puzzle along with it. The question of why empty space carries the particular, absurdly tiny energy it does, and no other. That older gap is the widest disagreement between theory and measurement anywhere in physics. The vacuum energy we can calculate, missing the one we observe by a factor with dozens of zeros in it. Before leaning too hard on any of this, the evidence deserves an honest weighing because it is far from settled. The strongest combinations reach about 4.2 sigma, which sounds crushing and means there is roughly a 1 in 20,000 chance the signal is a fluke of the statistics. Physicists have learned to be ruthless here, though. The line they draw before calling something real is 5 sigma, a 1 in 3 million standard, and the dark energy signal has not crossed it. Depending on which supernova catalog is folded in, the preference slides between about 3 and 4 sigma, and Deci's ruler on its own agrees perfectly well with a constant. The very largest figure, the 4.2, leans on one particular supernova sample. Choose a different and equally respected one, and the case softens. A result that depends on which good data you trust is a result to hold gently. There is also a quieter worry that the signal is not about the universe at all. Some cosmologists, George of Stathiou among the most prominent, have argued that the preference may spring from a disagreement between two data sets rather than from any new physics. When one supernova sample is swapped for a freshly recalibrated version of itself, the evidence for a changing dark energy can shrink toward nothing. And when the numbers are weighed with tools that reward the simpler explanation, the plain constant climbs back into favor. The honest summary is that the newest data have nudged the number, and no one yet knows whether the nudge is the universe speaking or the instruments disagreeing among themselves. This will not stay open forever, which is its own kind of mercy. More DESI data are already arriving, and the Euclid Space Telescope, the Rubin Observatory, and the Roman Telescope will each measure the expansion in their own way over the coming years. Within a decade, the hint will either harden into a discovery or dissolve back into the constant. We happen to be watching in the narrow window before we know which. We are living through the wobble, not the resolution, and that is a rare and uncomfortable place to stand. For most of the life of this question, the answer looked safe, and the safe answer was the gentle one. Now the steadiest number in cosmology is trembling at the third decimal place, and the discipline is to hold two things at once. The result is striking enough to reopen the fate of the universe, and shaky enough that wagering on it would be foolish. That tension feels more honest to me than any tidy answer would. For once, the sky has handed us a question we cannot yet close, and asked us to be patient with it. What matters for the ending is the direction of the drift. A dark energy that grows leads to the tear. A dark energy that holds leads to the long cold. A dark energy that fades leads somewhere we had stopped considering, back toward gravity's oldest ambition. So if the push that has spent billions of years driving everything apart is quietly losing its strength, what happens when gravity, patient and never fully beaten, finally gets its turn to answer? The oldest ending of all was pronounced dead in 1998, and the newest data may have brought it back to life. Long before anyone spoke of dark energy, the natural guess for how the universe ends was that gravity would win. Expansion would slow, halt, and reverse, and everything would fall back together into a single searing point. The discovery that the expansion is speeding up seemed to close that door for good. The hint that dark energy may be weakening has quietly cracked it open again. The whole question turns on a sign. The acceleration of the universe is set by the density of what fills it plus 3 times its pressure, with the vacuum energy working the other way. As long as that vacuum term stays positive, it drives the expansion outward faster and faster. But nothing in the mathematics forbids it from being negative. A negative vacuum energy does not push. It pulls, adding its weight to gravity rather than opposing it. And if the energy of empty space were ever to fade through zero and turn negative, the outward push would become an inward one, and the expansion would run out of momentum, stop, and begin to fall. You can see it in the expansion rate itself. That rate squared is fed by the density of everything the universe holds, and a negative vacuum energy enters that sum carrying a minus sign. As matter thins and the negative term grows more important, the expansion rate slides towards zero. It reaches zero at the universe's largest size, and the instant after, it has nowhere to go but down. The universe does not decide to collapse. Once the books turn negative, it simply can no longer hold itself open. A negative vacuum energy is not a desperate invention either. It is the natural home of much of string theory, which produces universes with a negative constant far more readily than the positive one we seem to live in. For decades, that mismatch has been a quiet embarrassment, a whole framework that keeps building the wrong kind of universe. A cosmos that is only temporarily positive and negative underneath would ease that discomfort at a stroke. This is not idle speculation, and that is part of what makes it striking. In 2025, a group of physicists took the same DESI and dark energy survey data we have been following and fit it with a particular model, an ultralight field paired with a cosmological constant allowed to be negative. The best fit preferred a negative constant. Read that way. The numbers say the universe will keep expanding for roughly another 11 billion years, reach its largest size, and then begin to contract. The whole span, from the Big Bang to the final collapse, comes to about 33 billion years, which would place the crunch itself some 20 billion years from now. By that reckoning, the universe is neither young nor ancient. It sits a little past its midpoint. Henry Tye, who led the analysis, pointed out that for 20 years, everyone had assumed the constant was positive and the universe would expand forever, and that the new data quietly unsettle that assumption. That number rests on one model among several, and it deserves to be held carefully. The raw DESI signal does not announce a crunch. It says the vacuum's push is not perfectly constant, and a negative constant is one way to read that, far from the only way. The same data, read through a different model, still allow the long expansion or even the tear. What has changed is only that the crunch, dead for a generation, is once again a serious answer rather than a discarded one. A collapsing universe is the Big Bang played in reverse, and it is not gentle. As space contracts, everything that expansion pulled apart comes rushing back together. Galaxies that have drifted for billions of years fall inward and merge. The afterglow of the Big Bang, which cooled to a few degrees above absolute zero as the universe grew, is squeezed and shifted back toward the blue until it becomes a furnace again. The background that reads 2.7 degrees above absolute zero today would climb back through thousands of degrees, then millions, then billions, retracing every stage of its long cooling in reverse. The sky, once cold and dark, brightens and heats until it outshines the stars, then until it melts them. The contraction does not ease near the end. It races, and the last structures are torn apart by heat and pressure rather than pulled together, a mirror of the tear run backward. Density and temperature climb toward infinity, and physics arrives once more at a singularity, the same wall of unknowing the equations meet at the very beginning. Here, the question in the title turns over into its second meaning. For the runaway tear, what lay beyond the end was nothing at all. For the crunch, there may be something, and that something might be a beginning. If the collapse does not stop dead at the singularity, if instead it rebounds, then the crunch of one universe becomes the bang of the next. The end and the beginning would be the same event, seen from two sides. Whether a collapse can truly rebound lies beyond anything our present physics can settle. A singularity is a place where the equations stop, not a passage they know how to describe. To turn a crunch into a bang, you would need whatever law governs the smallest and densest instant, the quantum theory of gravity we still do not have. A few candidate theories do predict a bounce, trading the singular point for a brief, unimaginably dense throat that the universe threads through and comes out the far side. Others predict only a wall. No one can yet say which. Richard Tolman, the physicist who first set cosmic thermodynamics on a rigorous footing, followed that thought all the way in 1934. A universe that bangs, expands, crunches, and bounces could do so again and again, an eternal chain of cosmic breaths. He wanted the idea to work. Instead, he found the flaw that has shadowed it ever since. The second law of thermodynamics, the same rule that gives time its direction, says the disorder of a closed system can only grow. Entropy does not reset at a bounce. It carries over, so each new cycle inherits all the disorder of the one before, and the cycles cannot be identical copies. They grow, each one longer and larger than the last. Tolman could even show the shape of it, a history of ever larger breaths rather than a steady heartbeat. Run the chain backward and the cycles shrink instead toward a first and smallest one, so an eternal past of bouncing is not on offer. Even a universe that repeats has to have begun somewhere. It takes a rare honesty to find the crack in your own most beautiful idea, and Tolman did exactly that. He gave the oscillating universe its mathematical dignity, and, in the same work, showed why it could not be the simple eternal engine people had hoped for. The dream did not die, though. Later physicists found ways around his objection, letting each cycle expand so enormously that its inherited disorder is spread impossibly thin, wiped nearly clean before the next contraction begins. The total disorder still climbs, but its density resets, and the cycle can run once more. What draws me to the crunch is what might follow it, more than the collapse itself. Every other ending we have traced leaves behind something that cannot be undone, a cold that never warms, or a tear that cannot heal. The crunch is the only one that holds out the possibility of starting over, of an end that is also a door. I do not know whether the universe takes that door, and no one does. But it is the single fate on the menu that is not, in the last accounting, a full stop. An ending you might survive by becoming the seed of what comes next is a different kind of ending than the others. For all its pull on the imagination, the crunch is still the underdog. Strip away the one model that favors it, and the balance of the evidence, even now, tilts the other way. Most of what we can measure still points to a universe that keeps expanding, thinning, and cooling without ever turning back. Which returns us to the quiet ending, the one with no crunch and no rebound, the long cold that simply goes on and on. So if the universe never collapses and never tears, but only expands into an ever colder emptiness, what does it even mean to call that an ending when there is no final moment for it to arrive in? The most likely ending is the one that never quite arrives. If the vacuum energy holds steady at -1, the way most of the evidence still suggests, the universe does not tear and does not fall back. It expands forever into an ever emptier dark, and it approaches a state where nothing can happen again without ever passing through a single moment where anything finally ends. Heat death is older than cosmology, and it was born in the age of steam. In the 1850s, physicists studying engines noticed that heat only ever flows one way, from hot to cold, and that every time it does, a little of the world's capacity to do work is lost for good. Rudolf Clausius gave that lost capacity a name, entropy, and stated its fate in a single sweeping line, that the entropy of the universe tends toward a maximum. Hermann von Helmholtz and William Thomson followed the thought to its end. If every process drains usable energy into uniform warmth, then far enough in the future, the whole universe must arrive at one flat temperature, with no difference left anywhere to drive anything. William Thomson, later Lord Kelvin, wrote of a universal tendency in nature toward the dissipation of energy, a slow leak in the world that no cleverness could ever plug. They called the end of it the heat death of the universe. It moves me that the death of everything was first glimpsed by people bent over boilers and pistons. They were trying to build better engines, and instead they found the expiration date of the cosmos written into the same equations. The universe, it seemed, was a kind of engine too, and every engine eventually runs down. What has always struck me is how well the verdict aged. It was reasoned out for a static universe, the only kind anyone pictured then, and it could have died when the universe was found to expand. The expansion only made it worse. A growing universe does not merely even out its heat, it dilutes and cools without limit. So the final sameness is not just uniform but frigid and all but empty. Modern cosmology took that old verdict and gave it a shape. If dark energy is a true constant, its density never changes, and a constant density feeds the expansion at a constant rate. When the Hubble rate holds steady, the size of space no longer grows by addition, but by multiplication. It doubles, then doubles again, then again, each doubling taking the same stretch of time. Written down, the scale factor climbs as A equals a naught times E raised to H times T, the exponential curve of de Sitter space, named for the astronomer who first solved for an empty universe ruled by lambda. The doubling takes something like 10 billion years at today's rate, and the horizon it builds sits a little under 16 billion light-years away. Steady push, endless doubling. Exponential expansion does something a gentler growth never could. It builds a horizon. Because distant space recedes faster, the farther away it lies, there is a fixed distance beyond which everything is already receding, faster than light can cross the gap, and nothing out there can ever reach us again. One by one, the galaxies drift across that line and wink out of causal contact, their light stretched and dimmed until it fades from every instrument. The time scale is vast but finite. In something like 150 billion years, the galaxies beyond our own bound neighborhood slip out of reach, and within a couple of trillion years, the last of their light fades from view entirely. Given enough time, every galaxy beyond that gravitationally bound island crosses over and is gone. What remains is an island of a few merged galaxies, alone in a darkness that grows without limit, its own stars burning down toward black embers. Push that forward far enough, and even the embers evaporate, and the matter that made them thins into a whisper of stray particles and faint radiation, all of it drifting at one uniform temperature. That sameness everywhere is what maximum entropy looks like. Nothing hotter than anything else, nothing left to flow, nothing left to build. No gradient means no work, and no work means no life, no thought, no motion of any kind that could set one instant apart from the next. There is a lonely footnote to this. Once every distant galaxy has crossed the horizon, any astronomer who arises in that far future will look out and see only their own island of stars, motionless against an empty sky. The evidence that the universe was ever expanding, ever larger, ever full of light, will have been carried beyond reach. The long cold erases even the record of everything that came before it. You might expect such a universe to settle at absolute zero, the perfect cold of nothing. It does not, and the reason matters. That cosmic horizon, like the edge of a black hole, carries a faint temperature of its own, worked out by Gibbons and Hawking in the 1970s. For our universe, it comes to about 2.3 times 10 to the minus 30 of a degree above absolute zero. That is 30 orders of magnitude colder than the microwave glow that fills the sky today. A coldness so near to zero that the gap looks like a rounding error. That floor is set by the expansion rate itself, the temperature running in proportion to the Hubble rate through the very relation Gibbons and Hawking found. As the universe settles into pure de Sitter and the Hubble rate levels off to a constant, the temperature levels off with it at that faint and permanent value. But it is not zero, and that floor will matter more than its size suggests. Strangest of all, this ending has no final moment. The rip ends at a definite instant, and so does the crunch. Heat death does neither. Entropy rises toward its maximum, but it approaches that ceiling the way a curve approaches a line it never touches, coming ever closer across an infinite stretch of time. You can push the mathematics arbitrarily far and never reach a stopping point. There is no last event, no closing tick, no moment you could point to and say, "Here it ended." The universe simply grows quieter and colder and emptier, forever, without ever finishing. The second law now shows what it has quietly been all along. The growth of entropy is the closest thing the universe has to a clock. Every process that marks time, a candle burning, a heart beating, a memory forming, runs on the flow of order into disorder. When entropy reaches its maximum and stops climbing, that clock stops with it. Time, as physics defines it, does not halt in some dramatic way. It simply loses anything to measure. With no change anywhere, there is no before and no after, no way even to tell that time is passing. The forward flow you feel at this very moment, tonight giving way to tomorrow, is that same rise in entropy, running quietly inside you. For a century and a half, the heat death has been the soberest guess anyone has for the end, precisely because it asks for nothing exotic, only that the second law keep doing what it has always done. And still, this ending unsettles me in a quieter way than the others. The tear is violent, and the crunch is a catastrophe, but both of them, at least, are events, with a shape and a finish. Heat death is not an event. It is a fading that never completes. There is something harder to hold in the mind about an ending that is really an endless approach, a universe that does not die so much as trail off past the edge of anything that could be called a story. The others are deaths. This is closer to a sentence with no last word, one that simply thins into silence and keeps going. What lies beyond an ending that never ends? The question begins to come apart in your hands. There is no beyond in time, because there is no final moment to be beyond. And yet the picture of perfect, permanent stillness has a flaw hidden inside it. That faint floor temperature, the fact that the vacuum never reaches true zero, means empty space is never entirely quiet. Something in it still stirs. So if the emptiest, coldest, most final state the universe can reach is still, very faintly, warm, then what is it that keeps moving in a place where everything was supposed to have stopped? Empty space never holds still. Not even the vacuum left behind at the end of everything, cooled to within a hair of absolute zero, ever fully stops moving. The stillness of heat death is a description of the average, and the average hides a restlessness that never switches off. To see why, you have to give up the picture of empty space as an empty container. Space is filled everywhere with quantum fields, and what we call a vacuum is simply those fields resting in their lowest possible state. But the lowest possible state is not a state of perfect rest. The uncertainty principle, the same rule Werner Heisenberg found for particles, forbids any field from holding a perfectly definite value and a perfectly definite rate of change at the same instant. A field pinned exactly to zero, steady and unmoving, would break that rule. So even at its calmest, a field must tremble, borrowing and returning tiny amounts of energy, never quite settling. Picture every point in space as a tiny spring that can never be brought fully to rest. Pluck it and it vibrates. Leave it alone and it still quivers with an irreducible minimum it cannot fall below. The vacuum is an endless field of these springs, each one humming at the lowest note it is allowed to hold, and the hum never stops anywhere, ever. Every one of them carries a residual energy equal to half of Planck's constant times its frequency, an amount you cannot drain away, cool out, or reach beneath. Physicists call it zero-point energy, the energy that remains after all the energy that can be removed has been removed. The vacuum is not the absence of everything. It is the quietest that everything is allowed to be. There is a second way to picture the same jitter. Energy and time obey their own uncertainty relation. So for a fleeting instant, the vacuum can borrow energy from nowhere, conjure a particle and its antiparticle, and repay the debt before the universe can register the loan. These virtual pairs flicker into being and vanish again everywhere, constantly, the froth on a sea that has no surface. Both pictures describe the same fact. The ground floor of reality is in motion, and there is no basement below it. None of this is a rumor from the far future. It is happening in the air of the room around you right now, and inside you, in every cubic inch of space your body fills, the fields humming at their lowest note and never once falling silent. If this sounds like a story that could never be tested, it has been, and the result is one of the stranger measurements in physics. In 1948, Hendrik Casimir worked out what should happen if you set two flat metal plates a hair apart in a perfect vacuum. Between them, only fluctuations whose waves fit neatly into the gap can survive, while outside, every fluctuation is free to press in. That leaves slightly less of the vacuum's churn between the plates than around them, and the surrounding fullness pushes them together, a force out of nothing that falls as one over the fourth power of the gap. Casimir reached that answer by adding up the energy of every fluctuation, a sum that runs to infinity both inside the gap and outside it, and then subtracting one infinity from the other. What survives is small, finite, and exactly what the plates feel. That two boundless quantities should leave behind a force you can weigh on a balance is the kind of thing that ought not to work and does. For decades it stayed a prediction on paper. Then, in 1997, Steve Lamoureux hung a delicate torsion balance in a vacuum chamber and measured that push directly, a force of about a billionth of a Newton, matching Casimir's formula to within a few percent. It still stops me what that experiment really weighed. It set the emptiest thing anyone could build onto a scale and found it pushing back. The pressure of nothing is real, and you can read it straight off an instrument. The Casimir push is not the only fingerprint. The same restless vacuum nudges the electron inside a hydrogen atom, shifting one of its energy levels by a whisper that shows up in the exact color of the light the atom gives off. That tiny shift was measured in the 1940s, and it agrees with the theory of a jittering vacuum to better than a part in a million. The emptiness has been checked again and again, and it is never empty. That restlessness follows the universe into the far future we traced a moment ago. The heat-death universe is not sitting at absolute zero. Its horizon radiates at that faint Gibbons and Hawking temperature, in proportion to the expansion rate, a thin warmth that fills all of space and never fades as long as the expansion continues. That warmth is the horizon's own version of the glow Hawking found at the edge of a black hole, pairs of particles born at the boundary, one drifting away and one falling inward as a trace of heat. So the final state is not a frozen calm. It is a bath, unimaginably cold and yet not quite at zero, and anything above zero is a thing in perpetual motion. Run that future forward far enough, and this bath is nearly all that is left. The black holes evaporate, the last stray particles decay or scatter past every horizon, and what remains is space itself, empty and expanding, holding little but its own faint glow. The universe ends, in a sense, as almost pure vacuum. And the vacuum is precisely the thing that refuses to sit still. This is what the word equilibrium has quietly meant all along. A gas sitting at a steady temperature looks perfectly calm from across a room, its pressure and temperature holding fixed. Up close, its molecules are a storm, flying in every direction at hundreds of meters a second, colliding billions of times over in the space of a heartbeat. Equilibrium does not mean nothing moves. It means the average does not change while the details churn without rest. Heat death is that same arrangement written across the whole universe, perfectly still on average and forever, endlessly busy underneath and forever. Stillness was always the wrong word for it. The universe does not go silent. It goes uniform, and uniform is not the same as finished. Once you accept that the vacuum is always simmering, a door opens that a truly frozen universe would have kept shut. In a system that never stops jittering, there is always some chance, however faint, of a fluctuation that runs against the grain. A patch of vacuum might, by pure accident, gather its trembling into a brief flicker of order, a few particles assembling where there were none, a momentary dip in the perfect smoothness. The chance of a fluctuation of a given size falls off exponentially, roughly as E raised to minus the energy it takes divided by the temperature. Make the fluctuation larger or the temperature lower, and the odds collapse toward nothing with terrifying speed. But collapse toward nothing is not arrival at nothing. To make it concrete, the air in a room could, in principle, rush by chance into one corner and leave the rest a vacuum. Nothing in the laws forbids it. It never happens because you would wait unfathomably longer than the present age of the universe to catch it even once. In a cosmos with no last moment, though, waiting far longer than the age of everything is no barrier at all. At a temperature of 10 to the minus 30 degrees, these events are staggeringly unlikely, their odds smaller than almost any number that appears anywhere in science. And yet staggeringly unlikely is a wholly different thing from impossible. The odds against even a small, orderly flicker are written with more zeros than there are atoms in the observable universe, the kind of unlikelihood that, across any finite span, is a flat impossibility for every practical purpose. The probability is tiny, and it is never quite zero. Movement alone would be a curiosity. What gives it weight is what an unlimited amount of time can do with the smallest and most reluctant motion. That single fact that the chance is small but never zero changes everything the moment you set it against the one resource this universe holds without limit, which is time. So if empty space keeps trembling forever, and forever is exactly what this cold universe has been given, what becomes of something that is merely almost impossible once it is offered an endless number of chances to happen? Give the universe long enough, and everything that can happen will happen, no matter how absurdly unlikely, and then it will happen again, without end. That sentence sounds like a mystic's line, yet it follows straight from two things we have already met: a vacuum that never stops moving, and a future with no last day. What turns those two facts into something staggering is a single idea about what disorder really is, worked out by a man who did not live to see it win. Entropy has a reputation for being murky, but underneath it is only counting. Ludwig Boltzmann saw that a hot, spread-out, disordered state and a cold, tidy, ordered one differ in a plain way. They differ in how many distinct arrangements of their tiny parts would look, from the outside, exactly the same. Take 100 coins. There is exactly one way for all of them to come up heads, a single perfect arrangement. Out of the more than 1,000,000 trillion patterns those 100 coins can make, that all heads pattern is the only one of its kind, while the patterns near an even split of heads and tails number in the hundreds of thousands of trillions. Order is rare because order has few arrangements. Disorder is common because disorder holds nearly all of them. Boltzmann pinned that insight to a single equation, the one now carved on his gravestone in Vienna. Entropy equals a small constant times the logarithm of W, the number of microscopic arrangements that share the same overall look. More arrangements, more entropy. The logarithm is there so that the entropies of two systems add up sensibly when you put them together. But the heart of it is that one letter, W, a raw count of possibilities. The constant out front, Boltzmann's constant, is fantastically small, which is why everyday entropies come out as sane numbers, even though the counts hidden inside them are astronomical. Entropy is not a substance or a fluid. It is a tally of how many ways a thing could be while still looking the way it does. Once you see entropy as counting, the second law stops being a commandment and becomes a near certainty. A system drifts toward higher entropy for the plainest reason imaginable. There are overwhelmingly more disordered arrangements than ordered ones, so if the parts are shuffling at random, they are overwhelmingly likely to land in a disordered one. Heat spreads out for the same reason. Gathering into a single hot corner is one arrangement among a near infinity that spread it evenly, so spreading is simply what almost always happens. The arrow points toward disorder the way a dropped marble finds the bottom of a bowl, by sheer weight of numbers. Stir a spoonful of cream into coffee and it never unstirs, for exactly this reason. The swirled together states outnumber the neatly separated ones so lopsidedly that random motion lands in one of them every single time. Because the second law is a matter of counting rather than command, it does not forbid the arrow from ever running backward. It only makes it staggeringly unlikely. A shuffled system could, by pure chance, land in one of its rare ordered arrangements. Heat could gather, a gas could bunch into a corner, a broken thing could leap back together. Nothing in the underlying laws rules it out. The chance of a backward step of a given size falls off exponentially as E raised to minus the size of the drop in entropy divided by that same small constant. For anything larger than a handful of particles, that probability is so small it might as well be zero. Might as well be, and yet is not. A probability that is small but not zero has an entirely different destiny when time is infinite. Suppose some event has one chance in a number with 100 zeros of occurring in a given stretch of time. In a finite universe, you would never see it, not once, not if you waited 1 trillion times the present age of the cosmos. But an infinite future does not offer 1 trillion tries or 1 million Google of them. It offers endless tries, one after another, forever. Multiply any chance that is not exactly zero by infinitely many attempts, and the result is not merely that the event happens. It happens infinitely often. Follow that where it leads, and the consequences turn dizzying. In the eternal, faintly warm vacuum of heat death, every arrangement of matter that is physically possible will, sooner or later, assemble itself by chance. A hydrogen atom would appear almost at once. A star would take a weight beyond imagining. A planet, a galaxy, a living cell would each take longer still. And given patience enough, and the universe is nothing if not patient, an entire ordered region indistinguishable from the one you are sitting in tonight. A small fluctuation might take a span you could almost write down. A whole cosmos might take a span next to which the age of everything so far rounds to nothing. The version of you reading these words, down to the last memory behind your eyes, would form again somewhere in that endless dark, not once, but an unlimited number of times. The rarer the thing, the longer the wait, and the wait is always finite against a future that is not. There is a cruel edge to that exponential. Because a larger drop in entropy is exponentially less likely than a smaller one, the universe will always, overwhelmingly, favor the smallest fluctuation that can do the job. If it is going to accidentally build something, it builds the least it can get away with. The grand, wasteful miracle of a whole ordered universe is fantastically less likely than the meager, minimal flicker that would just barely suffice. The cheapest way to conjure an observer who believes they are seeing a universe is to skip the universe entirely and assemble only the fleeting observer. That thought sits quietly for now. It does not stay quiet. The vertigo of this was not lost on Boltzmann. He was the first to look through his own equation and see what lay on the other side. Faced with the objection that his statistical universe should run backward as often as forward, he offered a startling answer. Perhaps the universe as a whole, across the largest scales and the longest times, sits quietly at maximum entropy, and the ordered world we see, the stars and the galaxies and our own improbable selves, is nothing but a rare fluctuation, a momentary dip in the smoothness that will one day smooth away again. He handed us the tool, and then he turned it on everything and suggested that all we call real might be a statistical accident. I find that a lonelier thought than any of the endings themselves, that the same man who taught us to count our way to certainty also showed how that certainty could dissolve the ground beneath everything we trust. It is hard to say these things about Boltzmann without feeling the weight of how his life ended. He suffered from severe depression and failing health, and in the late summer of 1906, on holiday with his family near Trieste, he took his own life. The old story says he died unrecognized, broken by colleagues who refused to believe in atoms, but that telling is too neat. His work was widely respected, and the great universities of Europe competed for him. What is true and quietly cruel is the timing. Within a couple of years, the reality of atoms he had spent his career defending was confirmed beyond argument, and he did not live to see it. There is something this picture quietly takes away, and it took me a while to see what. If order is only a matter of waiting, then order is not precious or chosen. It is merely rare, and rare is a smaller thing than meaningful. A star assembled by accident in the far future is, atom for atom, the same as a star born from a collapsing cloud, and yet one feels like a birth and the other like a coincidence. Beneath that unease sits a sharper problem still. If the laws allow entropy to fall as readily as they allow it to rise, if a backward step is only unlikely and never forbidden, then something we take entirely for granted suddenly has nothing left to explain it. So why, in all of our experience, does time run only one way, the past ordered and the future disordered, when the laws that govern every single particle do not seem to care which way it goes? None of the fundamental laws of physics can tell the past from the future. Write down Newton's equation for a moving particle, or Maxwell's equations for light, or the Schrödinger equation for a quantum wave, and each of them runs exactly the same whether you let time flow forward or backward. Replace the symbol for time with its negative, and nothing breaks. The mathematics does not know which way time goes. The reason is almost embarrassingly plain. Newton's law depends on acceleration, on how a velocity changes, and reversing the clock twice over leaves acceleration untouched, so the same forces trace out the same paths. Maxwell's equations carry the same symmetry, and even quantum mechanics keeps it once you take the mirror image of its complex numbers along with the clock. You can see the symmetry in a simple picture. Film 2 billiard balls colliding and glance at the movie. Run it forward or backward, and both versions look perfectly ordinary. A physicist could not tell which way the film was threaded. Now film a glass falling and shattering on the floor. Run that backward and it turns absurd, shards leaping off the tiles and gathering themselves into a whole glass that hops up into a waiting hand. Every particle in that shattering obeys the same reversible laws as the billiard balls, and yet the whole event has an unmistakable direction. The arrow lives in the crowd, never in any single member of it. Arthur Eddington gave this asymmetry its name in the 1920s. He called it the arrow of time, and he traced its source to entropy rather than to any single particle. Time has a direction, he argued, because entropy has a direction, and entropy's direction is the one thing in physics that refuses to run backward in our experience. Everything else the laws permit in both directions. This single habit, the growth of disorder, seems to point only one way. We already hold half the answer, from Boltzmann. Entropy grows toward the future because disordered states vastly outnumber ordered ones, so blind shuffling almost always lands in disorder. But notice what that argument leaves undone. It works just as well toward the past. Take any ordinary moment, and the same counting insists entropy should be higher a moment earlier too, because disorder is more likely in every direction you look. Statistics alone gives you a valley with no preferred slope. To turn that valley into an arrow, you need one more fact, that the past was not ordinary at all. The universe began in an extraordinarily ordered, low-entropy state, and the arrow points away from that beginning. A sharp objection to all of this arrived in the 1870s from Joseph Loschmidt. If the microscopic laws are truly reversible, he said, then for every process that raises entropy, there is a mirror process, reached by reversing the velocity of every particle that lowers it. Reversal is not forbidden by anything. It is written into the laws as plainly as the forward direction. Boltzmann's reply, as the story is told, was blunt. If you believe you can reverse every velocity and watch entropy fall, then go ahead and try it. For 80 years, that sounded like a taunt, a thing that could never be done. Then, in 1950, Erwin Hahn did it. He took a sample of atomic nuclei, each one a tiny magnet spinning in a strong field. Because the field is never perfectly even, each nucleus spins at a slightly different rate, and the whole population fans out, their little magnetic arrows spreading until they point every which way, and the ordered signal they once made together fades to nothing. That fanning out is disorder rising, entropy climbing, order seemingly lost. Then Hahn sent in a single carefully tuned pulse of radio waves that flipped every spin, in effect reversing the sign of the very motion that had scrambled them. And the spins began to unfan. The ones that had raced ahead now fell behind. The ones that had lagged now caught up. And at a precise moment every arrow pointed the same way again, and the vanished signal came roaring back. It is the same trick a line of runners could play on a track. Set them off at different speeds and they spread down the lane, the fast ones pulling ahead, the pack smearing out. Blow a whistle and have every runner turn on the spot and run back at the same speed, and after the same interval, they all arrive at the start line together, the spread undone. The order was never destroyed by the spreading. It was only stored in who was where and moving how fast, and if you can reverse the motion, you can call it home. Order reassembling itself out of apparent chaos, on command, in a laboratory. It is one of the quietly astonishing things I know of, that you can stand in a room and watch entropy run backward, watch a scrambled thing unscramble, because the scrambling was never truly random, only hidden. That experiment earns a small and permanent awe from me. It is the closest anyone has come to answering a dead man's dare, and the answer it returns is yes, you can, for a moment, if you are gentle enough, and the world will hold still. But the echo carries its own lesson about why this never happens on its own. Hahn's pulse reversed the spin's motion in the external field, and it did nothing to reverse the far messier interactions of the spins with one another. Those small, uncontrolled couplings kept right on scrambling, and no single pulse can flip them. So the echo returns a little weaker each time, and after long enough, it does not return at all. The order leaks into a web of correlations too tangled to reach, and once it is there, it is gone for good. That leaking is the second law's real content. Reversal is never forbidden. It is only that the information needed to run a process backward spreads, almost at once, into so many particles and so many correlations that no experiment could ever round it all back up. Entropy rises because gathering the scattered past into one place again becomes impossible faster than anything else in nature, even though no law forbids the gathering. Physicists have a name for that leaking now. They call it decoherence, and it is why the quantum world, so fond of being in many states at once, looks solid and single to us. It is also the enemy every quantum computer is built to fight, since a machine that computes by holding its parts in delicate step is racing that same one-way spill of information into everything around it. Just how fast it becomes impossible is hard to overstate. A single air molecule in this room, tracked as it bounces from neighbor to neighbor, would have its path thrown off by the faint gravitational tug of a single electron at the far edge of the galaxy after only a few dozen collisions. The tiniest disturbance anywhere is enough to make the future of a crowd unrecoverable. To run the room backward, you would need to reverse every particle with a perfection that the universe itself will not allow. This is no failure of our cleverness or our instruments. It is a limit built into a world where everything touches everything else, however faintly, so that no patch of it can ever be sealed off cleanly enough to be wound back. There is a single strange exception, and honesty asks that I mention it. Deep in the weak nuclear force, in the decays of a few rare particles, nature does show a whisper of a preference for one direction of time, measured in the laboratory. But the effect is so faint and touches so few processes that it comes nowhere near explaining why glasses shatter and never unshatter. The everyday arrow is still, overwhelmingly, a matter of counting and correlations rather than of any law that points. The arrow we live by, then, is borrowed. It is not stamped into the deep laws, which run both ways with perfect indifference. It comes almost entirely from one fact, that the universe began in a state of exquisite order and has been unwinding from it ever since. Cosmologists call that starting assumption the past hypothesis, and nearly everything we feel as the flow of time is balanced on top of it. That turns the whole mystery into a single, harder question, the one Loschmidt was really aiming at all along. So if the direction of time is nothing more than the memory of an ordered beginning, then why did the universe begin so ordered at all? And what becomes of time's arrow in a future where that memory has finally run out? The second law of thermodynamics is not, strictly speaking, a law of nature at all. It behaves like one, it predicts like one, and no one has ever caught it failing. But underneath, it is something stranger, a report about how the universe happened to begin, wearing the costume of a law. The man who first exposed that disguise was a friend and senior colleague of the man who had spent his life defending it. By the 1870s, Boltzmann believed he had done something magnificent. Starting from nothing but molecules bouncing off one another under ordinary mechanics, he had written down a quantity, he called it H, that could only ever fall as the gas evolved. The quantity was, in essence, the sum over all the molecules of their probability times the logarithm of that probability, a bookkeeping of how spread out the gas had become. Since a falling H means rising entropy, he seemed to have proven the second law from pure dynamics, to have conjured the one-way flow of time out of the timeless laws of collision. Joseph Loschmidt did not believe it, and he was right not to. Loschmidt was older than Boltzmann, a careful experimentalist who had been the first to estimate the size of a molecule, and the two men were close. In 1876, almost as an aside at the end of a paper about something else, he pointed out a hole that could not be patched. Take any evolution in which Boltzmann's H falls and entropy rises. Now reverse the velocity of every molecule at the final instant. The laws of mechanics permit this new motion exactly as much as the old one, and along it, H rises and entropy falls. For every path to disorder the mechanics allow, they allow its mirror image running straight back to order. A proof that entropy must always increase cannot be true if the same laws also permit it to decrease. The objection had in fact first appeared in print 2 years earlier from William Thomson, the same Kelvin we met at the heat death, but it was Loschmidt who pressed it on Boltzmann directly, and it has carried his name ever since. Something in Boltzmann's derivation, then, was not pure mechanics. Loschmidt had found exactly where. Buried in the proof was an assumption Boltzmann had barely noticed making, that the molecules about to collide have velocities completely uncorrelated with one another, a condition with the forbidding name of molecular chaos. The assumption sounds innocent, and it is quietly one-directional. Think of the opening break in a game of pool. Before the cue ball strikes, the racked balls sit in a tidy triangle and share no history, their motions uncorrelated. A moment after, they are flying apart along paths finely tuned to one another by the collision, their motions deeply correlated. Molecular chaos holds looking forward, before collisions, and breaks, looking backward, after them. Boltzmann had quietly assumed the arrow at the very start, in a clause he had taken for harmless bookkeeping. This is the real teeth of Loschmidt's paradox, and it reaches far past one 19th century proof. You cannot squeeze an arrow of time out of laws that have none without slipping a time-asymmetric assumption in somewhere. Every derivation of the second law ever written carries one, and when you hunt it down, it always proves to be the same creature in a fresh coat. Somewhere, quietly, the argument assumes the system started in a special, orderly, uncorrelated state, and then shows only that it becomes less special from there. Follow that assumption to its root, and you arrive at the universe itself. The reason entropy rises everywhere, the reason eggs break and stars burn and we remember yesterday and not tomorrow, is that the entire universe began in a state of staggeringly low entropy, and everything since has been the long slide away from it. Physicists gave that founding condition a plain name, the past hypothesis. It is not a law and not a theorem. It is a fact we assume about one end of time, because without it, nothing else makes sense. That is a peculiar kind of explanation, one that explains by quietly assuming the very thing that is most puzzling. Inflation, the theory of a violent early stretching of space, is often said to account for the smoothness, and in some ways it does. Yet many argue it only relocates the mystery, since inflation itself has to begin in a low entropy patch of its own. The question has a way of surviving every answer thrown at it. Some have tried a bolder escape, proposing that time runs in both directions away from a single low point, so that another universe reaches backward from the same beginning, its inhabitants calling our distant past their future. It is an elegant idea, and it still leaves the low point itself unexplained. Comfort drains out of the picture when you ask how special that beginning had to be. Roger Penrose worked out the odds. Of all the ways the matter and energy of the observable universe could have been arranged at the start, the fraction as orderly as ours is about 1 in 10 raised to the power of 10 to the 123. That is not a number anyone can picture. Writing out merely its exponent, the 10 to the 123, would take more zeros than there are particles in the entire universe. The ordered beginning we owe everything to is very nearly the least likely way a universe could possibly start. There is a twist in why that beginning counts as ordered at all. Our intuition says the early universe, smooth and nearly featureless, is the very picture of high entropy, an evened out sameness with nowhere left to go. But gravity turns that intuition inside out. For matter under gravity, smooth and spread out is the rare, low entropy state, and the likely, high entropy state is one clumped and collapsed into black holes. The Big Bang counts as astonishingly ordered precisely because it was so smooth, a taut uniformity that gravity has been busy lumping together ever since. That single appetite of gravity, its taste for clumping, is why the smooth early cosmos could give birth to stars and galaxies at all. Order had somewhere to fall from. The strangeness of this is hard to overstate. The arrow of time is the most reliable fact in all of human experience. It underwrites memory, cause and effect, growth and decay, the difference between doing and undoing, the entire shape of a life. And it rests, in the end, on a boundary condition we cannot explain, an initial order so improbable that its unlikelihood dwarfs every large number physics has ever produced. we do not know why the universe began so ordered. We only know that if it had not, none of this, including the one asking the question, would be here to notice. You can feel that arrow right now, in the plain fact that you can recall the beginning of this sentence and not its end. That certainty is so total it seems to need no explaining, and it is exactly the thing physics cannot yet ground in anything deeper than a beginning it cannot account for. There is something I find almost tender about how this flaw came to light. Loschmidt did not set out to wound his friend's great work. He raised the objection briefly, near the end of a paper on a gas in a gravitational field, and moved on. Boltzmann took it seriously enough to spend years answering it, and in answering it he was forced to surrender the dream of a proof and admit that the second law is only overwhelmingly probable, leaning on how things started rather than on how they must be. The friendship survived. The dream of deriving time's direction from timeless laws did not. For the story of how everything ends, this flaw has a sharp edge. If the arrow of time exists only because we are still falling away from that ordered beginning, then the arrow is not permanent. The universe nears heat, death, and entropy approaches its ceiling. The fall runs out. The memory of the ordered past fades toward nothing, and with it, the very direction of time grows faint and then meaningless. And there is a darker turn still waiting. Loschmidt showed only that a decrease in entropy is allowed. A quieter, stranger theorem, worked out in those same years, shows that in a universe with no end, such a decrease is not merely allowed. It is certain, again and again, forever. So if reversing the arrow of time is not just possible but, given endless time, certain, then what becomes of a universe that has already reached its final stillness, when the mathematics insists that it must, sooner or later, gather itself back together? The final stillness is not final. A universe that reaches heat death is condemned, by a theorem no one has been able to break, to gather itself back together and then to do it again and again without end. Everything that has ever existed, every star and every face, returns, not once, but countless times. That theorem is one of the most elegant and most unsettling results in all of physics, and it came from Henri Poincaré in 1890, in a prize-winning study of how the planets move. He was thinking about a bounded system, a set of particles confined to a finite space, obeying reversible laws. He proved something that seems at first to be impossible. Given enough time, such a system must return arbitrarily close to any state it has ever occupied. And having returned once, it must return again, infinitely many times over. Poincaré laid it out in his prize essay, and 3 decades later Constantine Carathéodory made it fully rigorous with the mathematics of measure. It has stood, unshaken, ever since. Its proof is almost unfairly simple. Picture the complete state of the system, the position and motion of every particle at an instant, as a single point in an abstract space of every possibility. As the system evolves, that point traces a winding path through the space of possibilities. A deep result called Liouville's theorem says the flow of these points behaves like an incompressible fluid, never piling up and never thinning out, only moving around. The flow can bend and stretch and fold in the most tangled ways, yet it can never overlap itself in the same instant, and it can never leak out of the finite room it lives in. An incompressible flow trapped in a finite space cannot keep finding fresh, unvisited territory forever. Sooner or later it must return close to ground it has already covered, and so the system comes back close to where it was. Now set that theorem loose on the dead universe. We saw that heat death is not truly still, that the vacuum keeps trembling, and that in infinite time any fluctuation, however rare, must occur. Poincaré's theorem sharpens that from a probability into a certainty of a particular kind. A universe of particles rattling around in a bounded space of possibilities will not merely happen to produce order now and then. It will return, arbitrarily closely, to every ordered arrangement it has ever held. The galaxies reassemble, the stars reignite, and a morning very much like this one dawns again. The cold, spread-out equilibrium is only a plateau the universe rests on for an unimaginably long while before it wanders, by sheer chance, back down into order. Think of a drop of ink released into a glass of clear water. It spreads and thins until the water is a uniform gray and its order looks gone for good. The recurrence theorem promises that if you waited long enough, the ink would, of its own accord, gather itself back into a single dark bead, exactly where it began. Nothing forces this to happen. Nothing forbids it either, and across endless time, unforbidden is all it takes. You will want to know how long this takes, and here the numbers stop meaning much of anything. The physicist Don Page set out to calculate it in a paper with the arresting title, Information Loss in Black Holes and Conscious Beings. He treated the whole observable cosmos as a box and asked how long before its quantum state returns to what it is right now. The answer he wrote down is 10, raised to the power of 10, raised to the power of 10, raised to the power of 10, raised to roughly 2. A tower of exponents 4 stories tall. Numbers like this shatter the tools we normally reach for to grasp size. The strangest thing about that number is what happens when you ask what units it is written in. Years? Seconds? The lifetime of the present universe? It does not matter in the slightest. A number with a tower of exponents that tall is so vast that multiplying it by 1 billion, or by the count of every atom in the cosmos, or grinding it down to the tick of the Planck clock changes nothing anyone could ever notice. The choice of unit, which governs every other measurement in all of science, simply dissolves into the size of it. The entire history of the universe so far, its 14 billion years, rounds to 0 against a weight like that. To live out that whole history, then repeat it once for every atom in your body, then once more for every atom in the earth, would not carry you a single meaningful step closer to the recurrence. The number swallows every effort to approach it. Honesty asks for one caveat here, and it is a subtle one. Poincaré's theorem needs a bounded space of possibilities, and a universe that expands forever is not bounded in any straightforward sense. But the accelerating universe hands us a boundary anyway, in the horizon we met at heat death. That horizon holds only a finite amount of information, an entropy of around 10 to the 122, and a finite store of states means the recurrence still returns on a time scale set by the exponential of that entropy. The order comes back through the vacuum itself rather than through the old machinery of collisions, a chance thermal fluctuation, or a quantum tunneling event assembling a fresh island of order out of the faint warmth of empty space. Some cosmologists treat this recurrence as a warning rather than a wonder, a hint that any theory which predicts it may be quietly telling us that something in our picture has gone wrong. The worry is that a universe which rebuilds conscious observers by random fluctuation, over and over, might rebuild far more of the wrong kind than the right. That suspicion has teeth, and it will not stay a suspicion. We arrive, then, at another answer to the question in the title, and it may be the most vertiginous of them all. What lies beyond the end? It is not the nothing of the tear, and not the single fresh start of the crunch. It is everything, over and over, forever. The end becomes a turn in a loop with no exit rather than a wall or a door, and every star that ever burned, every word ever spoken, and this exact quiet moment all lie somewhere ahead of us as well as behind, waiting to come around again. I cannot decide whether this is the most hopeful idea in the whole story or the most desolate. Everyone you have ever lost returns. So does every loss. The same joys and the same griefs turn on an endless wheel, with no version of any of them ever being the last. This exact night, awake in the dark with these very thoughts, is not a one-time entry in the cosmic ledger, but a recurring one. The idea had already haunted thinkers like Friedrich Nietzsche, who felt the vertigo of an eternal return with no equations to lean on, and the mathematics, when it finally arrived, did not soften the thought so much as sharpen it. There is a thought that surfaces here and refuses to leave. If every configuration returns infinitely often, then the words before and after begin to lose their footing. A moment that has happened countless times already and will happen countless times again is not first or last or original in any firm sense. An ending that is followed by the same beginning, endlessly, is not really an ending at all. The recurrence theorem does not only threaten heat death, it quietly threatens the idea that time runs in a direction, or that any event is ever truly finished. In a loop that turns forever, the real question is no longer when the universe ends, but whether ending is a word that can survive the shape of a circle. Boltzmann had brushed the recurrence aside by pointing to how staggeringly long it takes to arrive. A younger mathematician refused to be satisfied with that answer. Ernst Zermelo saw in Poincaré's theorem something far worse than a curiosity to be waved away with a big number. He saw a flat contradiction of the second law itself. If entropy must eventually fall, as the recurrence guarantees, then how can it be a law that entropy always rises? So if the universe is fated to unwind its own ending again and again, then can the second law of thermodynamics, the one rule we leaned on to give time its direction, really be a law at all, or only a habit that holds until the recurrence comes to break it? The recurrence takes something more precious than the ending. It takes the direction of time itself, and once that is gone, the word ending is almost nothing left to point at. This is the deepest and strangest turn in the whole story, the place where the ordinary meaning of an ending quietly comes apart in our hands. A young mathematician named Ernst Zermelo was the first to press this to its edge in 1896. He was an assistant to Max Planck in Berlin, careful, formal, and skeptical of the whole idea that heat could be reduced to bouncing molecules. Zermelo was no crank. He would go on to become one of the founders of modern set theory, the logician who framed the axiom of choice and proved that any collection of numbers can be well ordered. He trusted proofs, and the proof in front of him looked airtight. He took Poincaré's recurrence theorem, which he accepted as plainly correct, and laid it beside Boltzmann's second law and showed that the two could not both be literally true. If the recurrence holds, then entropy cannot climb forever. It must come back down, again and again, as the universe returns to its earlier states. A quantity that rises and falls in endless cycles is not a quantity that only ever increases. And so, Zermelo concluded, if the second law is an absolute truth, then the mechanical picture of matter, molecules obeying reversible laws, must be false. Boltzmann's reply was cutting, and beneath the sharpness it conceded the point that mattered. He did not deny the recurrence. He agreed it was real, and that entropy would indeed fall as often as it rose over a long enough span. What he denied was that the second law had ever been a law of always. It was, and had only ever been, a law of almost always, a statement about probability. He compared Zermelo to a gambler who works out that a run of 1,000 ones on the dice is not impossible, and then, having never seen such a run, declares the dice must be loaded. The recurrence is that run of 1,000 ones. It happens. You simply do not live long enough to watch. But look at what Boltzmann had to surrender in order to save his law. Picture the entire history of an eternal universe as a single curve, entropy plotted against time. For almost all of that endless span, the curve runs flat along the top, at maximum disorder, the equilibrium of heat death. Every so often, unimaginably rarely, it plunges into a deep valley, a fluctuation of order, and then climbs back to the top. The depth of a valley sets how rare it is, since the probability of a dip falls off as E, raised to minus the size of the drop in entropy, so the deeper the order, the more staggeringly seldom it comes. We do not live on the flat stretch because nothing can live there. Life, structure, thought, all of it needs a slope, a difference to feed on. We live on the wall of one of those valleys, on the long climb back up toward equilibrium, and the direction of that climb is what we call the future. Every valley has two walls, and the second wall is where this grows hardest to hold. On one side runs the slope we climb, on the other, its mirror. On the far side of the low point we climbed from, there is another slope, running the other way. An observer who happened to arise on that far wall would experience their own arrow of time pointing in the opposite direction to ours. Their entropy would rise the way ours does, toward what we would call the past. They would remember what we call the future and await what we call the past, and they would be every bit as right as we are. There is no fact of the matter about which way time truly flows. There is only which slope you happen to be standing on. This cuts to the bone, and it has to do with memory. To lay down a memory is itself an act that increases entropy, so a mind can only ever remember in the direction of lower entropy, toward the valley floor it climbed from. Every observer's past is, by the very way memory works, the low entropy end of their own slope. That is why the far wall observer's past is our future. Each of us remembers downhill. The arrow is not a feature of time. It is a feature of us, of the direction in which we are able to form a record at all. The certainty you feel right now, that this sentence follows the last and leads to the next, is not really a report about time. It is a report about the direction your own memories happen to run. Boltzmann himself followed the thought all the way to this place. He suggested that across the eternal universe, the arrow of time need not point the same way everywhere, that different regions, born from different fluctuations, would each carry their own local direction, their own past and future, quietly disagreeing with one another. The arrow we are so sure of, the one thing that seems beneath all argument, becomes a parish custom, true only inside our small valley and meaningless outside it. Poincaré himself had felt the chill of it. In his popular writing, he mused that the recurrence meant the world was not headed for a single final death. Instead, it circled endlessly back to states it had already known, an eternity of return in place of an ending. The word ending loses its grip entirely here. An ending is a place time arrives at, a last thing after which there is no after. But if time has no single direction, if every valley is a beginning for the observers climbing out of it, and every peak an ending only when seen from below, then there is no last thing anywhere. The universe does not head toward a final state and stop. It rises and falls forever, with no privileged moment that counts as the end, and no privileged direction in which to look for whatever lies beyond it. The question we began with, what is beyond the end, is not answered by the recurrence, so much as quietly dissolved by it. I have gone back and forth on whether this is a bleak idea or a strangely gentle one. If nothing is ever the last, then no loss is final, though neither is any beginning, and the universe becomes a thing with no plot at all, only weather. There is a sadness folded into how this all came out. Zermelo was not wrong about the mathematics. The recurrence really does forbid a quantity that climbs forever. Boltzmann was not wrong either. The second law really is only statistical. Both men were right, and the thing that gave way between them was the hope that time's direction is stamped into the world at its deepest level. There is a bitterness in Boltzmann's reply that is hard to miss, the tone of a man guarding his life's work against a clever young logician, and half losing the larger point even as he won the argument. Even Planck, who sided with his young assistant, could not stomach a second law that was merely probable, and he turned to the puzzle of glowing hot matter, hoping to find a firmer proof, a search that would help pry open the door to quantum theory. The dispute reshaped physics, and it left the arrow of time resting on nothing more solid than a lucky beginning and the slope we happen to occupy. And yet Boltzmann's rescue carries a poison in its own cup. If we are a fluctuation climbing out of a valley, then we ought to ask what kind of fluctuation we most likely are. The cheapest one, we already saw, is the smallest that will do the job. A whole universe with 14 billion years of real history behind it is an extravagantly expensive fluctuation. Something far smaller and far more common would serve just as well to produce this single moment of experience, this one instant of a mind that believes it remembers a past. And the harder you insist that your past is real, the tighter the logic pulls, because insisting is precisely what the cheaper fluctuation would do too. So if we are most likely something far smaller than an ordered universe, the least the vacuum could assemble to fool us, then who exactly is asking this question, And is there any real past behind this moment at all, or only the fresh, false memory of one? If you take the fluctuation picture at its word, then you, right now, are almost certainly not a person living in a 14-billion-year-old universe. You are a single brain that flickered into being a moment ago, out of the noise of empty space, complete with the false memory of having read the sentence before this one. The universe you think you remember never happened. In a heartbeat, you will dissolve back into the dark. The experience would be seamless. A Boltzmann brain does not feel like a Boltzmann brain. It feels exactly like being you, on an ordinary night, certain of a whole life stretching out behind it, because certainty and memory are cheap to fabricate, and fabricating them is the entire trick the fluctuation performs. This is the cliff the long argument about time zero has been walking toward. We said the ordered world might be a rare fluctuation, a dip in the eternal equilibrium. We said the cheapest fluctuation is always the smallest one that gets the job done. Put those together and ask what the job is. The job is to produce a conscious observer having exactly the experience you are having now. And the smallest, cheapest way to produce that experience is to build just the observer for a single instant and skip the cosmos entirely. This flickering ghost has a name. We call it a Boltzmann brain, after the man whose fluctuation hypothesis first opened the door to it, though he never used the phrase. Boltzmann's own version imagined whole worlds bubbling out of the equilibrium, not lone minds. The sharper and crueler form, that the very cheapest thing to fluctuate is a single observer and nothing else, is a modern twist, and it makes the problem far worse. Arthur Eddington had gestured at the notion back in the 1930s, and it has quietly haunted physics ever since. It was raised in its present shape in 2002 by Lisa Dyson, Matthew Kleben, and Leonard Susskind, in a paper with the frank title, Disturbing Implications of a Cosmological Constant. They pointed out that a universe ruled forever by dark energy, the eternal de Sitter state we reach at heat death, is a thermal system with a faint but real temperature, and in such a system, given forever, anything at all can fluctuate into being, a mind included. The reason the brains win is the same exponential we have met again and again. The probability of a fluctuation falls off as E raised to minus the drop in entropy it takes to make it. A single brain, with its few pounds of ordered matter, is an astronomically small dip. A whole universe, with its low entropy beginning and its billions of years of consistent history, is a dip beyond all comparison deeper. The ratio of their probabilities is the exponential of that difference, a number whose exponent is so large that ordinary language simply gives out. To hang rough figures on it, the ordered matter of a single mind is a dip of perhaps 10 to the 40, while a universe like ours sits at a dip past 10 to the 100. The distance between those two exponents is the distance between the two chances, and it is not a distance anyone climbs back across. Real observers, people like the one you believe yourself to be, can only appear during the brief early chapter when stars and galaxies exist, a window of perhaps 100 billion years, generous but finite. Boltzmann brains can appear across the entire infinite future. Take a fluctuation rate as tiny as 10 raised to minus 10 raised to 50, multiply it by an eternity, and it still buries the finite crop of real observers without a trace. Finite against infinite is never a close contest, no matter how rare each phantom is. Then the argument turns on itself, and that is what saves us from it. Suppose you accept the conclusion that you are almost certainly a Boltzmann brain. Then your memories are false, including your memory of the physics that led you to the conclusion. Your reasoning is the momentary churn of a random fluctuation with no reason to be reliable about anything. The very argument that convinced you that you are a Boltzmann brain was produced by a brain that has no business being trusted about anything at all. Sean Carroll put it precisely. A theory that predicts you are probably a Boltzmann brain is cognitively unstable, unable to be both true and rationally believed at the same time. It devours its own evidence. Physicists, then, do not conclude that they are Boltzmann brains. They conclude the opposite, that any theory or any model of the cosmos which predicts a world drowning in Boltzmann brains has thereby shown itself to be broken. The Boltzmann brain becomes a test, a tripwire strung across the space of possible theories. A healthy cosmology is one that produces ordinary observers like us in comfortable abundance and keeps the fluctuating phantoms vanishingly rare. Many otherwise reasonable models fail that test, and their failure is counted as a serious mark against them. This is no sleight of hand. It is one of the rare places in physics where a statement about minds and memories feeds straight back into which equations we are allowed to keep. Getting the counting right is harder than it sounds, and here the honesty has to come in. In an infinite universe, there are infinitely many ordinary observers and infinitely many Boltzmann brains, and comparing two infinities is not something the mathematics does cleanly. You need a rule, a measure, for weighing one endless population against another, and no one has found a measure that everyone accepts. The whole problem is tangled up with that unsolved question. One influential answer from Kimberly Boddy, Sean Carroll, and Jason Pollock holds that a vacuum simply sitting in a stationary quantum state never undergoes the sharp, discrete fluctuation events the paradox requires, so that without something to make the wave function jump, no brain is ever assembled at all. Others reply with plain probability, noting that the moment you take seriously that your experience is coherent and lawful and full of consistent records, the odds of being a random brain collapse toward nothing. The matter is not settled. It is taken seriously, and it is open. But grant the problem its force for a moment, because it does something to the ending that nothing else in this story has done. The universe that would breed the endless swarm of Boltzmann brains is the gentle one, the eternal de sitter cold that expands forever and never stops. The quiet ending, the one that seemed the safest of all, is the cognitively unstable one, the factory of phantoms. And so a strange preference has taken hold among some cosmologists. They would rather the universe truly end. If our vacuum is not the final word, if it can decay to a lower state and shut the whole thing down before the fluctuation clock runs long enough to fill the cosmos with false minds, then we are rescued from the paradox by a real ending. Don Page went so far as to ask, in the title of a paper, whether our universe is likely to decay within 20 billion years, and to argue that, for the sake of our own coherence, it had better. His half-serious estimate was that to keep real observers ahead of the phantoms, our vacuum should give out on roughly the same timescale we have already been handed. I find that turn quietly astonishing. For the whole first half of this story, the ending was the thing to fear, the tear and the crunch and the long cold. Now a final, decisive ending arrives as a kind of mercy, the one thing that can stop the universe from dissolving the meaning of being an observer at all. So you can breathe. The argument does not leave you a hallucination. It leaves you holding a tool, and the tool says that any universe which could make you doubt your own memory this badly is a universe our theories have gotten wrong somewhere. There is a lesson folded into that which I have been slow to take in, that permanence is not the same as safety, and that a cosmos with no exit can be a stranger and lonelier prospect than one that quietly closes its own door. The most frightening future is not the one that ends. It is the one that never does. So if the safest way out of this whole paradox is for the universe to bring itself to a real and final stop, then what could possibly reach into the emptiness of space and switch off a cosmos that shows every sign of lasting forever? The switch that could end everything is not out among the stars. It is inside empty space, in the possibility that the vacuum we live in is not the true floor of the universe, only a ledge above it. If that is so, then the most complete ending of all is not a fire or a collapse. It is a change in what empty space is allowed to be. We have treated the vacuum as the bottom of the barrel, the lowest energy state the fields can hold. But lowest that we know of is not the same as lowest that exists. Picture the energy of a field, the Higgs field that lends particles their mass, as a landscape of hills and valleys. We are sitting in a valley, and it feels like the bottom of the world. Yet across a ridge, out at enormous field values we have never probed, the landscape may drop again into a deeper valley, a lower vacuum than ours. If it does, our vacuum is only metastable, a resting place that could, in principle, give way to the deeper one. It cannot climb the ridge, since the vacuum has no energy to spend on the climb. Instead, it can tunnel straight through the barrier, the same quantum trick that lets a particle pass through a wall it could never scale. Somewhere in the vast reaches of space, at some instant in the vast reaches of time, a tiny bubble of the deeper vacuum tunnels into being. It works like the first bubble in a pot about to boil, or the first speck of ice in water chilled below freezing. Below a certain size, the seed cannot pay for its own surface, and it collapses and vanishes. The reason is a contest of scales. A bubble's surface grows with the square of its radius, while the energy it liberates grows with the cube. So a small enough bubble is all costly surface and no reward, and a large enough one is ruled by the volume that pays. Past that critical size the balance tips, and it becomes profitable for the bubble to grow. Its wall sweeps outward, and because the energy released drives it, it accelerates until it is moving at very nearly the speed of light. The rate at which such a bubble appears at all is set by the exponential of a quantity Coleman named the bounce, an exponent so large and negative that the arrival of even one bubble anywhere nearby takes very nearly forever. Sidney Coleman worked out the physics of this in the 1970s, and with Frank DeLucia, he folded gravity into the picture in 1980. What they described is the most thorough catastrophe the equations will allow. Coleman did not spare his readers the horror of it. He pointed out that the new vacuum would be not merely hostile to life, but hostile to the very structures that any conceivable life or chemistry would need, a cleaner erasure than any weapon could manage. Inside the bubble, the Higgs field settles at a new value, and that value sets the scale of every particle's mass. Shift it even a little, and you rework the fine ledger that lets a proton and an electron settle into a hydrogen atom. Move it far enough, and the periodic table has no entries left at all. No chemistry, no matter of the kind we are made from. The wall does not shatter things and leave the pieces. It converts the old vacuum into the new one, rewriting the rules as it passes, and everything built from the old rules is quietly unmade. Here the title's question turns over into its third meaning. What lies beyond this ending is not nothing and not a repetition. It is a different physics, a cosmos running on other laws, in which our kind of matter has no place to be. And because the wall arrives at the speed of light, it comes with no herald. The light that would announce its approach arrives in the same instant as the wall itself. There would be no tremor, no warning, no moment of knowing. One instant the world is as it is, and the next it is not, with no gap between in which anything could be felt. No ship could flee it, since nothing outruns light, and the wall carries the light of its own coming. What unsettles me is that this may not be idle theory. When the Higgs boson was finally measured, its mass came out near 125 billion electron volts, and the heaviest particle we know, the top quark, near 173. Feed those two numbers into the equations and follow the Higgs landscape up to enormous energies, and the potential does something quietly ominous. It turns over. A deeper valley opens far out in the field, which would make our vacuum metastable after all. And the strangest detail is where those numbers place us, almost exactly on the knife edge, between a stable vacuum and an unstable one, so close to the line that physicists call it near criticality and do not know what to make of it. No one knows why we should sit so near that edge. Some suspect it is a clue, a fingerprint left by physics we have not found, a hint that the Higgs mass is set by some deeper rule we cannot yet read. The same equations that raise the possibility also place it almost unimaginably far off. A metastable vacuum sitting this close to the edge is extraordinarily long-lived. The estimated time before a bubble would nucleate anywhere in our observable surroundings is not measured in billions of years, or even billions of billions. It runs instead to a 1 followed by hundreds of zeros of years, a weight beside which the present age of the universe is nothing at all. It leans, too, on the Standard Model, holding all the way up to energies we have never tested, and almost any new physics waiting out there could push the vacuum back to safety. This is a thought experiment about what empty space might secretly be, not a forecast of the morning. And there is an odd mercy tucked into the physics of it. An ending that arrives at light speed, with no signal running ahead of it, is one you could never dread in the moment, because there is no moment to dread it in. It may be the least fearful catastrophe conceivable, precisely because it can never be lived through as one. There is a reason this particular ending belongs here, right after the swarm of Boltzmann brains. A vacuum that decays is exactly the escape we were looking for. If our vacuum is false, and it gives way after some enormous but finite time, then the universe does not run forever in its gentle de Sitter cold. It comes to a real and total stop before the fluctuation clock can fill it with false minds. The most complete catastrophe imaginable doubles as a rescue, the one clean way to end a cosmos that otherwise would refuse to end at all. This is a strange thing to hold in one hand. The deepest destruction the laws permit, a wall of altered physics racing outward at the speed of light, might be the very thing that keeps the universe honest, that stops it from dissolving into an eternity of phantom observers. Ending and mercy arriving in the same event. For most of us, the vacuum is the very picture of safety, the one thing that cannot break because there seems to be nothing in it to break. To learn that the emptiest place is where the deepest fragility hides, rearranges something in how I look at a clear night sky. There is even a thread running back to where this story first turned. If dark energy is not a fixed constant, but a field slowly rolling downhill, as the newest data faintly hint, then it is a near cousin of a false vacuum, a landscape the universe may still be descending. The question of how everything ends and the question of what fills empty space keep proving to be the same question wearing two faces. But grant, for a moment, that the vacuum does decay, that the bubble sweeps out and the old laws end. Even that is an ending that happens inside physics, one set of rules giving way to another set of rules. It leaves a deeper question standing, perhaps the last one this whole story can ask. If every ending we have found, the tear, the crunch, the cold, the recurrence, even the collapse of the laws themselves, still takes place somewhere inside space and time, then is there anything at all that could lie beyond the end of physics itself, or does the question finally run out of ground to stand on? There is a way for the universe to end and begin again in the same motion, with no bounce and no singularity to pass through. It turns on a single strange idea, that in the far enough future, the words big and small quietly stop meaning anything at all. If that is true, then the coldest, largest, emptiest end of one universe is indistinguishable from the hottest, smallest, densest birth of the next. Follow the heat-death universe all the way to its limit. Every star has died, every particle of matter has decayed, and even the black holes, which hold almost all the entropy there is, have finished evaporating away into faint radiation. What remains is a universe of pure light, of massless things, photons and gravitons drifting through an endless, expanding dark. And a universe made only of massless things has lost something we never think to question. It has lost the ability to measure itself. A ruler needs something with a size. A clock needs something that ticks, something with mass that can sit still and count out a duration. Light has neither. A photon has no rest frame and no proper time. From its own point of view, it is emitted and absorbed in the very same instant, having crossed no distance and spent no time at all. It is a strange thought that a beam of light, in a sense, never ages, that the whole stretch, from the first star to the last, could pass, for a single photon, in what it would call one instant. In a cosmos with nothing but light, there is no yardstick anywhere, no way to say that one region is larger than another, or that one span is longer than another. All that survives is the shape of the light cones, the pattern of what can reach what the angles rather than the sizes. Physicists call that stripped-down geometry conformal. In the language of the equations, a conformal geometry is one where the metric, the rule that assigns distances, is fixed only up to an overall stretching factor. Multiply every distance by any smooth function you like, and the physics of massless things does not notice. It keeps the shape and throws away the scale. Roger Penrose looked at that scale-free far future, and at the scale-free instant of the Big Bang, where the universe was also almost pure radiation, and saw that they might be the same kind of thing. Both are geometries in which size has no meaning. So he proposed to glue them together. Take the infinitely stretched, frozen future of one universe, and, since scale is meaningless there, allow yourself to shrink it. Take the infinitely dense, blazing Big Bang of a new universe and allow yourself to stretch it. Because energy and size scale in exactly inverse ways, shrinking the cold future turns it hot, and stretching the hot birth turns it cold, and at the seam, the two match smoothly. The end of one universe becomes the Big Bang of the next, joined by a quiet rescaling of what counts as large, with no violent bounce in between. Penrose calls each of these universes an aeon, a full history from a Big Bang to an infinite, cold, radiation-only end, and he strings them into an endless chain, each aeon flowing conformally into the one after it. He named the idea conformal cyclic cosmology and laid it out in a book called Cycles of Time in 2010. Its real beauty is what it repairs. We saw earlier that the Big Bang was mysteriously, almost impossibly ordered, low in exactly the gravitational entropy that gravity loves to build. In Penrose's scheme, that order is not a miracle to be explained. It is an inheritance. Penrose had long argued that the order of the Big Bang shows up as the vanishing of one particular piece of the curvature, the Weyl curvature, that measures how tangled and clumped gravity has become. His crossover forces that curvature to zero at every new beginning, so the smooth, featureless end of the previous aeon, where gravity has spent everything and nothing is clumped anymore, becomes the smooth, featureless start of ours. The low entropy beginning we could not account for is simply the tidy deathbed of the universe before. It even offers to do the work of inflation, the theory of a violent early stretching that most cosmologists use to explain why the sky looks so evenly the same in every direction. In Penrose's picture, that sameness is just carried over from the calm, smoothed-out end of the aeon before, with no separate burst of expansion required. Even the entropy problem that sank the old bouncing universe is answered here, in a strange way. Almost all the entropy of a mature universe ends up locked inside its giant black holes, and when those finally evaporate, Penrose argues, the information they swallowed is truly gone, and the bookkeeping of possible states resets, so the next aeon can begin as ordered as ours did. It is a controversial move, since it asks us to accept that black holes destroy information for good, but it lets the cycle run without the disorder piling up from one aeon to the next. A theory this bold has to say something we can check, and Penrose, with Vahigur-Zadjan, tried. They argued that violent events in the previous aeon, collisions between giant black holes, would leave faint rings in our cosmic microwave background, concentric circles of unusually smooth temperature. Later they pointed to what they called Hawking points, warm spots that would be the last gasps of supermassive black holes from the aeon before, bleeding across the seam. For a while, it looked as though the far sky might carry a signature of a world older than the Big Bang. Honesty has to speak plainly about what came next. At least 3 independent teams went back to the same data and reanalyzed it, and each found that the circles and the points were entirely consistent with ordinary cosmic noise with the plain standard model and no previous aeon at all. The claimed signals did not survive the scrutiny. As evidence for a universe before ours, they came to nothing. I want to be careful and fair about where this leaves conformal cyclic cosmology. It is a minority view held by few, and it carries real unsolved problems. No one has shown how to fix the rescaling in a single, unique way, so the crossover itself is not yet pinned down. The scheme demands that information be permanently destroyed inside black holes, which a great many physicists reject. And it needs fresh physics to hand mass back to a reborn universe, including a hypothetical particle Penrose calls the Erebon, which no experiment has ever glimpsed. There is a particular courage in an idea like this, pursued for decades by a man who could have coasted on a Nobel Prize and a lifetime of celebrated results, and who instead keeps chasing a lonely, beautiful geometry that most of his colleagues have quietly set aside. This is a deep idea from one of the deepest geometric minds alive, and it is also, for now, unconfirmed and largely unaccepted. Both of those are true at once. Still, of all the answers we have gathered to the question in the title, this is the only one that says, without flinching, that beyond the end there is a beginning. Not the same beginning played again, as the recurrence would have it. A wholly new one, a fresh aeon with its own long history, its own stars and its own endings, connected to ours only through that thin conformal seam. I find something quietly moving in the fact that our best mathematics cannot rule it out, even as our best observations cannot confirm it. The end of everything and the beginning of everything may be, at the deepest geometric level, the very same surface, seen from 2 sides. There is a version of this that feels almost like consolation, and I try to hold it lightly, without leaning my weight on it. It would mean that no ending in this whole story is ever the last word, that the universe keeps writing fresh volumes forever, none of them a repeat, each with its own light. But every ending in this half of the story, the recurrence, the phantom minds, the reborn aeons, leans on one assumption we have never once questioned. All of it takes for granted that time truly goes on forever, that the future is truly infinite. Take that assumption away, and the recurrence never completes, the phantoms never accumulate, and the aeons never begin. So before we ask what lies beyond the end, we have been quietly assuming there is an endless supply of time in which to look for it, and it is time, at last, to ask whether that is even true. For all of this, the honest truth is that we do not know how the universe ends. And there is a harder admission underneath that one. We do not even know whether the word forever, which the last several turns have leaned on so heavily, describes anything real. It helps, out here near the frontier, to sort what we have been saying by how firmly we really hold it. Some of it is measured, read almost directly off the sky. The universe is about 13.8 billion years old. It is expanding. The expansion is speeding up right now, and the thing we call dark energy makes up close to 7/10 of everything there is. The second law of thermodynamics holds in every experiment anyone has ever run. The proportions of the lightest elements match what the first few minutes after the Big Bang should have cooked up, and the afterglow of that beginning glows at almost exactly the temperature the theory predicts. We have caught gravitational waves rippling out from colliding black holes, exactly as the equations foretold a century before we could hear them. We have watched galaxies spin too fast for their visible matter and mapped the unseen mass that holds them together. These are not guesses. They are the bedrock the rest is built on, checked 1,000 ways. Above the bedrock sits a layer that is openly contested, where good measurements disagree with each other. Whether dark energy is a fixed constant or a thing that slowly changes, the question Desi reopened is not settled, sitting well below the 5 sigma bar that physics holds out for before it calls anything real. Whether our vacuum is truly stable or only metastable depends on particle masses we are still pinning down, and on physics we may not yet know. And even a number as basic as how fast the universe is expanding today is in open dispute. That 5 sigma bar physics insists on is not mere fussiness. It is the scar tissue of a field that has been fooled before by promising 3 sigma signals that later melted into nothing, and the evolving dark energy hint, for all its weight, still sits on the wrong side of it. That last one deserves a moment, because it is a quiet lesson in humility. There are 2 respected ways to measure the expansion rate. One reads it from the afterglow of the Big Bang and arrives at about 67 kilometers per second for every megaparsec of distance. The other climbs a ladder of nearby exploding stars and arrives at about 73. Those 2 numbers ought to agree, and they do not, by more than 5 times the size of their stated uncertainties. Better telescopes, the James Webb among them, were expected to close the gap, and instead they sharpened it. There are recent hints of the 2 values creeping toward a middle figure near 70, but that claim is itself disputed, and the matter is far from closed. If we cannot yet agree on how fast the universe is expanding this very afternoon, we should wear our certainty about its death 100 billion years from now very lightly. And then there is the top layer, the tallest and the least secure, which is where nearly everything dramatic in this story lives. Every one of the endings we have walked through is up here. The tear, the crunch, the long cold, the recurrence, the phantom minds, the reborn aeons. Not one of them has been confirmed. They are extrapolations. The known laws carried far past anything we have ever tested, out to energies we cannot reach, and across spans of time, beside which the whole history of science is a single breath. To feel the reach of it, consider that organized science is roughly 400 years old, and here we are making confident-sounding claims about events 10 to the 100th power of years away. It is a little like a mayfly, alive for one afternoon, forecasting the slow grinding of a continent. None of that makes the extrapolations useless. They are the best reasoning we have, and thinking far past the data is how physics has often found its way forward. But there is a difference between a well-motivated guess and a measured fact, and keeping that difference in plain sight is the whole of the discipline. Propping up the strangest of these ideas is a single assumption we never once stop to examine, that time itself simply goes on without end. The recurrence needs an eternity to complete. The Boltzmann brains need an eternity to gather. Penrose's endless aeons need an eternity to unfold. Take away the quiet premise that the future is truly infinite, and the whole apparatus loses its footing. But forever is not something we have measured, or ever could. It is the boldest extrapolation of them all, an entire eternity conjured out of a few thousand years of written records. We are, in a real sense, an eye-blink reasoning about the everlasting, and the everlasting is precisely the thing an eye-blink can never check. And there are real ways the future could turn out finite after all, a vacuum that decays and shuts everything down, a dark energy that fades and lets the cosmos fall back into a crunch, or some feature of a quantum theory of gravity we do not yet possess. We also have no working account of gravity at the quantum scale, and that gap sits exactly where the beginning and the possible end of time both live. Reasoning about the ultimate fate while missing the physics of the ultimate scales is a little like sketching the far bank of a river no one has ever crossed. The cleanest map I know of this uncertain country comes from the astrophysicist Katie Mack, who laid out 5 ways the universe might end in a book with the plain, unhurried title, The End of Everything. She walks through the crunch, the long cold, the rip, the vacuum decay, and the bounce, and she does something I admire. She refuses to crown a winner. She holds all 5 at once, gives each its fair due, and is honest that the evidence does not yet choose between them. She also writes about the death of all things with a warmth and a dark humor that make the vastness feel companionable rather than crushing. That refusal to force an answer is not a weakness in the work. It is what honesty looks like at the very edge of what we know. I find a strange steadiness in all this uncertainty, and it took me a while to learn to trust it. We have spent this whole story chasing the end of everything, and the truest thing we can say is that we do not know which end is coming, or whether the story even has a last page. That could feel like a failure. It feels to me more like an invitation, a reminder that the largest question we are able to ask is still wide open, still waiting on measurements not yet made. There is a kind of respect in being told the plain truth about the limits of what is known, rather than being handed a confident story that quietly has to be walked back later. You came to this with a simple question: what is beyond the end? And the most honest gift I can offer is a truthful map of how little we are sure of, rather than a tidy answer, and of how much room that still leaves for wonder. But strip away every assumption we cannot check, every extrapolation into the unmeasured dark, and something is left standing, small and solid. There is one part of the ending that is not a theory about the far future at all. It is happening now, in front of our instruments, in this decade. The expansion is accelerating. Galaxies are slipping, one by one, beyond the reach of any signal we could ever send. The horizon is quietly closing. It does not lean on any of the 5 endings being the right one. It is simply the raw fact of the acceleration, ground out in the data month after month, the one prophecy in this whole story that we do not have to take on faith. Whatever the final shape of the end, a piece of it is already underway, and we can watch it happen. So if we set aside every ending we cannot yet confirm, and look only at what the sky is doing right now, what does it mean that the universe has already begun, measurably and without any hope of reversal, to disappear from its own view? The end of the universe is not an event waiting somewhere in the far future. It is a process, and it is already running, and you could measure it tonight if you had the right instrument pointed at the right patch of sky. We have spent this whole story imagining distant cataclysms, and the most certain part of the ending has been happening quietly the entire time, in this decade, on this ordinary evening. To see it, you have to separate two things we usually let blur together. There is the universe we can see, and there is the universe we can reach, and they are not the same size. The visible universe is enormous, a sphere some 46 billion light-years across in every direction, filled with light that has been traveling toward us since near the beginning. But seeing a galaxy and being able to get to it are entirely different matters. The universe we could still reach, the region we could send a signal to or travel to if we left this very instant at the speed of light, is far smaller, and it is shrinking. Behind it is the acceleration we have been circling all along. Distant space is not sitting still. It is expanding, and the farther away a galaxy lies, the faster the space between us and it grows. This is Hubble's simple rule, that recession speed rises with distance. In symbols, the speed is just the Hubble rate multiplied by the distance. So, at the distance where that product reaches the speed of light, roughly 14 billion light-years out, a galaxy is receding as fast as light itself travels. Push any farther, and the gap widens faster than light can ever cross it. No signal we send will catch up. Nothing about this breaks relativity, since the galaxy is not moving through space faster than light. The space itself is simply stretching between us. A little beyond that distance lies the cosmic event horizon, near 16 billion light-years, and it is a true point of no return. Anything past it is gone to us for good, unreachable no matter how long we wait. The number attached to this is what unsettles me. Of all the galaxies we can see tonight, the great majority are already beyond that horizon. The dividing line falls at a redshift of about 1 7/10, and the sky is crowded with galaxies stretched far past it. By common estimates, something like 94% of the galaxies in our visible universe are already unreachable, already on the wrong side of the line where no message and no traveler could ever arrive. We can still see their light, ancient light that left them billions of years ago. But that light is a photograph of a place we can never touch and never contact again. They have already left us, in every sense that matters, while still shining in our telescopes. Point a telescope at almost any faint smudge in a deep field image, and you are very likely looking at a place that has already passed out of our future for good, a light still arriving from a shore we could never sail to. Nor does the horizon hold still. Every moment, as the expansion accelerates, more galaxies cross that line and slip out of reach, quietly, one after another, forever. They do not vanish in an instant. As a galaxy nears the horizon, its light stretches toward ever longer, redder wavelengths, dimming and cooling until it fades below anything any instrument could catch, like a voice dropping too low to hear. The disappearance is gradual, and it is complete, and it cannot be undone. The sphere of what we could ever touch is contracting around us as we speak, at a rate the equations lay out precisely, and not in some far-off epoch we will never live to see. The universe is not waiting to end. It is ending, in the only way this branch of the story allows, by cutting its own threads one at a time. The rate is not dramatic on any human clock. Galaxies do not wink out night by night. But it is steady, and it is measured, ground into the numbers, the way a clock's hands move too slowly to watch, and yet never once stop. What is disappearing is not matter. The galaxies are not being destroyed. They go on shining wherever they are. What is vanishing is connection, the possibility of reaching or being reached, the web of causal contact that once, in principle, tied every part of the cosmos to every other. The ending here is not a fire and not a collapse. It is a slow, measurable severing, a universe drawing apart from itself until each island is left alone. It is the loneliest kind of ending, and in a way the gentlest, an emptiness that arrives with no violence at all, one lost connection at a time. Of all the ways to end, this is the one that most resembles grief. The distant galaxies still there in the photograph and already beyond any reach. This full emptying takes a long stretch by human reckoning, something like 150 billion years before the last galaxies beyond our own bound group are carried away. But 150 billion years is not the far future in the way a rip or a crunch would be. It is a road we are already well onto, its first miles behind us. What is left for us at the end of it is a single merged galaxy, the Milky Way and Andromeda and their small companions drawn together into one, adrift in a dark with nothing else in view. There is a further turn to this that I find quietly staggering. Lawrence Krauss and Robert Scherer worked out what the sky will look like to observers in that emptied future, and the answer is a kind of forgetting. Once the distant galaxies have all crossed the horizon and their light has stretched away into nothing, a civilization looking out will see only its own island of merged stars motionless against a black and empty sky. The expansion will be invisible to them. The afterglow of the Big Bang will have faded past any detection. Every piece of evidence that the universe was ever larger, ever younger, ever full of light, will have been carried beyond reach. They will conclude, reasonably and wrongly, that they live on a single static island that has simply always been. Krauss and Scherer gave the idea a title that lands like a quiet bell, the end of cosmology, meaning not the death of the universe so much as the death of our ability to understand it. The science itself has an expiration date, written into the same expansion it studies. That reframes where we stand in a way I have not been able to put down. We happen to be alive at a legible moment, old enough that the universe has built stars and minds, young enough that the evidence of its whole history is still streaming into our telescopes. The book of the cosmos lies open and readable right now, and it is slowly closing. 1 trillion years from now, the same universe, running on the very same laws, will be unreadable, its own past quietly erased from the inside. We are reading over its shoulder in the one brief chapter when the words are still on the page. It is a strange and undeserved piece of luck to arrive in the narrow window when the cosmos is both old enough to hold observers and young enough to remain legible to them. Earlier, and there would be no us. Later, and there would be no evidence at all. And this is the thought I want to carry into the quiet. The force doing all of this, the accelerating expansion, the steady climb of entropy, the arrow of time we can never run backward, is not a distant abstraction that happens only to galaxies. It is the same physics that governs the cooling of a cup of tea on your table, the warmth leaving your body into the room around you, the one-way passage of this very evening. The ending is not only out there in the emptying dark. It is running, right now, at every scale, including the smallest and nearest one there is. You do not have to travel to the edge of the visible universe to witness the end of everything. A version of it is unfolding in the room with you, in the slow drift of heat and order that no hand has ever reversed. So if the same law that is quietly emptying the entire universe is also the law unfolding inside your own chest as you breathe, then what does the end of everything have to do with the warmth of a single body in a dark and quiet room tonight? Let me answer that question as plainly as I can, because it has a plain and quietly beautiful answer. The end of everything has everything to do with the warmth of your body in a dark room tonight, and I mean that as physics and not as poetry. It is the same law, the same second law of thermodynamics we have followed all evening, running inside you at this very moment, exactly as it runs across the whole of the cosmos. Your body is warmer than the air around you. Right now, without any effort and without any notice, it is giving off heat, a steady, invisible glow of warmth radiating from your skin into the cooler room, flowing the one direction heat always flows, from the warmer thing to the colder one. You are shining, softly, in infrared light, a lamp the darkness cannot see, but a simple camera could. Something close to 100 watts of it pours off you, hour after hour, the same as a bright old bulb. And every bit of that warmth, as it spreads into the room and never gathers back, raises the entropy of the world by a small and exact amount. The very same ds, greater than or equal to 0 that carries the universe toward its long cold, is written into the heat, leaving your hands and your face into the quiet dark. You are, in the language of physics, a small and temporary island of order in a universe sliding toward disorder. Erwin Schrödinger asked, in a slim and famous book written in the middle of the last century, how a living thing manages that at all, how it holds its exquisite order together while the second law is busy pulling everything else apart. His answer was that life does not break the second law. It obeys it, only more cleverly than a stone does. A living body draws in ordered energy, in food and warmth and light, and it pays for its own fragile order by pushing disorder back out into its surroundings, as heat, as breath, as the warmth now leaving you into the room. You keep your shape by helping the rest of the world come apart a little faster. Schrödinger wrote his small book at a time when no one yet knew what carried the order of life from one generation to the next, and his question helped send a generation of young physicists searching until they found that order written into the twist of a single molecule. You are an eddy that holds its form only because the river keeps pouring past it. The atoms that make you tonight are not the ones that made you a decade ago. They have flowed through you and moved on, and still you have stayed yourself because you were never really the atoms. You were the pattern they fell into for a while, a standing wave in a long river of matter and heat. There is a turn in this that I did not expect when I first started down this road. The very same arrow of time that is ending the universe is the thing that hands you this evening. the reason this moment feels like it is passing, the reason the night has a direction, the reason you can remember the beginning of this story and feel yourself moving toward its end, is that entropy is rising in the room and in the cosmos and in you all at once. Take that away. Hold the second law perfectly still, and there is no flow of time, no before and no after, no experience, no now. The same climbing disorder that will one day empty the whole sky is the very thing that lets there be a tonight at all, a warm and breathing moment that belongs to you. Everything you have ever cherished sits on that same slope. To grow, to learn, to love, to hold a memory, to miss someone who is gone, every one of them is entropy rising somewhere. A little order in one place paid for with a little disorder in another. The arrow that dooms the cosmos is the same arrow along which a life is even possible. I find something steadying in that, and I have carried it a long way to be able to say it to you. We spent this whole journey looking for what lies beyond the end, and we found tears and crunches and endless colds, recurrences and phantom minds and reborn universes, and a great deal of honest uncertainty about every one of them. But the ending was never only a far-off thing waiting to be feared. It has been here the entire time, gentle and near, in every breath you take and let go, in every cup of tea that cools on a table, in the plain fact that this evening moves forward and will never come again. The universe is not ending somewhere else, at some other time. It is ending softly, right here, in the warmth of you, and that same softness is exactly what it means to be alive. There is one more thought I want to leave with you before the quiet. For a brief while, on a small, warm world, the universe folded itself into a shape that could look outward and wonder how it all ends. That shape is you. The cosmos, through a few pounds of ordered matter kept warm against the cold, woke up just enough to ask the largest question there is and to feel something about the answer. That the universe can do that at all, even once, even for a lifetime as short as a breath against the ages, seems to me a stranger and finer thing than any of the endings we chase tonight. For the length of this one evening, the cosmos has been asking, through you, what becomes of it in the end, and feeling something tender about its own question. That is not a small thing to have been. So, for a little while now, there is nothing to solve and nothing to fear. Your body is warm and quiet, and that warmth is slowly, kindly leaking out into the room, the way it always has and the way it always will. Your breath goes out, carrying a little heat and a little disorder away with it, and then it comes back in, out and in, the smallest rhythm of the same vast process that moves the stars. Far away, on a scale too large to feel, the very same thing is happening to the whole of everything, unhurried, across spans of time in which this entire night is less than the flicker of a single heartbeat. You came asking what is beyond the end. Perhaps the truest answer, the one you can hold in your hands tonight, is that beyond every ending we managed to find, there was always this, a small warmth, a quiet breath, a single now. Let the great cold of the far future stay the far future's concern. Here, this evening, there is warmth enough and time enough, and it is yours. There is a deep and gentle comfort in being so small and so warm and so briefly here, held inside the same quiet law as the galaxies. Thank you for spending this stretch of the night with me, for following a question this large, all the way out to its far edge and back again to your own warm hands. It has been a real gift to think it through beside you. There is nothing left to chase tonight, and nowhere you need to be except exactly where you are. You can let the questions rest where they lie. You can let the warmth leave you slowly into the dark, the way it is meant to, the way it always has. One more breath out, and the ending asks nothing of you now, nothing at all, only that you rest. And whenever you are ready, you can let yourself drift down into sleep, small and safe, and held inside the same unhurried law that is carrying the whole universe, and you along with it, gently home. Good night.